Hello guys, how are you today? Sorry for that, I found a microphone in my house and I thought it would be funny to start off the AS Physics full revision with this mic. I'm not going to be using it for the full video, just for the introduction. So now I'm going to get rid of the mic. Sorry for that. Now we're back to normal. Just a warning, I might use the mic sometimes in the video if I get bored from explaining. And I feel like you too might get bored, so I'll boost both our moods using this. So what is my plan? Basically, we have AS Physics, we have chapters in waves and thermodynamics. The main chapters we have are chapters 1, 2, and 3. They didn't specify specific sections. Let me just double check. Oh no, excuse me, never mind. They did specify the sections, so I'm just gonna write them down. So for chapter 1, we only have 3 sections, which are sections 1.1 and 1.2, as well as 1.3. So, yeah, so it stops at question number 12. They didn't specify specific questions. So what I'm going to be doing is I'm going to be solving all of the questions from the required section. So without further ado, let's get started, okay? What does it say here? So in question 1, from section 1.1, it tells us to define density. Sorry for that. Now, what exactly is density? Basically, from its equation, you know that density, denoted by rho in physics, it's mass over volume. So, very simply, what is the definition of mass? Mass, it's in like physical terms, it's the measure of the quantity of matter. So, mass, you say it's the measure of quantity in matter. Okay, then it's what in a given volume, so divided by the volume. So how would you define density? Density, very simply, is the measure of quantity in matter in a given volume. You write this and you will get the full mark. Now we'll move on to question 2. What does it say? A metal solid ball has a radius of 2 centimeters. So in physics, we don't like to not use SI units. We always prefer to use the SI units. What's the SI unit for centimeter? It is meters. So I'll change it by dividing by 100. So I'll get 0.020 meters. A mass of 90 grams. 90 grams, you cannot accept it as well. So you need to change it to kilograms. So that would be 90 times 10 to the power of minus 3 kilograms. So they said, what is in kilogram per meter cubed? So they want the density of the ball in kilogram per meter cubed. So I have the mass and I have the radius. I can find the volume of the ball. And it's a solid ball. The ball is a what? It's a sphere. So what is the volume of a sphere? Very simply, the volume of a sphere, it's 4/3 pi r cubed. So I have everything I need in order to find the density. The density is equal to the mass, which is 90 times 10 to the power of minus 3, right? kg, divided by what? Divided by the volume, which is 4/3 pi times the radius. What's the radius? We said 0.020 cubed. Okay, so I'll take my calculator. 90 times 10 to the power of minus 3 divided by 4/3 pi times 0.020 to the power of 3. Now, only cube the radius. We don't want to cube everything. Only we're cubing the radius. So you put it on your calculator. And to the nearest integer, they want us to round it. I got 2,600. Oh, sorry, excuse me for this. 2,686 kg per meter cubed. Okay, that's it for question 2. Now we'll move on to question 3. What does it say? A solution is prepared by mixing 30 grams. Again, we cannot deal with this, so that's going to be 30 times 10 to the minus 3 kg of glycerol. They gave us the density. Again, the density is not an SI unit. 1.26 gram per centimeter cubed. Okay, and then they gave us with 10 grams of density. 10 grams of water. What did I say? 10 grams of water. And the density of water is 1 gram per centimeter cube. You know what? Since they're not putting the SI units, we don't need to necessarily change them in this equation. They're looking for the density of the mixture. Very simply, the density of the mixture, since both these densities are in gram per centimeter cubed, we'll look for it and we'll find it in gram per centimeter cubed. Now we know density is mass over volume. You cannot add the two densities. That's not going to work. You need to find the total mass and divide it by the total volume. So the total mass, it's going to be equal to what? It's going to be equal to 30 plus 10 grams, which is how much? Which is 40 grams. But now here's the issue, the volume. The total volume, I need to find volume of one plus volume of the other. I have the mass over here, I have the density. If density is mass over volume, then volume is mass over density. So it's going to be 30 grams divided by 1.26 plus what? Plus 10 grams divided by 1. So you add them together and you should get a total answer of 33.8 approximately centimeter cubed. So this is the volume. Now I have the total mass, I have the total volume, I can find the density. So it would be 40 grams divided by 33.8, I got an approximate answer of 1.18 gram per centimeter cubed. Okay, so that's it for question 3. We'll now, we finished section 1.1, we'll now move on to section 1.2, which is about pressure. The figure below shows the same block resting on its smallest side A at first, and then on its largest side A prime. How do the forces F and F prime compare after this adjustment of the block? Now, what is the force that's acting on the block in all these cases? It's its weight. Does the weight of the block change if I move its position? For example, yourself, if you are sitting upright or if you're laying down on your bed, does your weight change? No, it does not change. So what does this mean? This means that the force F, it's equal to what? It's equal to the force F prime. Now, does this logic, does it apply to the pressure? Very simply, the answer is no. It does not apply to the pressure. Now I'm using the microphone. Why does it not apply to the pressure? Very simply, we need to define pressure. Pressure is equal to what? It's equal to force over area. If my force stays the same, if I look at the surface area that's touching the let's say table or like whatever it is under the block, here this area is smaller than this area that's touching the block here. So for sure this would have what? It would have a greater pressure because the area is smaller. Whereas here this would have a smaller pressure. That means pressure P, it's greater than what? It's greater than pressure P prime. They ask you to explain why. It's because the surface area A is smaller than the surface area of A prime. Okay. So basically that's it for question 4 part A and B. We'll now move on to question 5. A car rests on 4 tires and each tire is in contact with the ground over an area of 140 centimeter cube. Or sorry, excuse me, squared. I don't know why I said cube. They gave us the pressure of what? If the pressure exerted by each tire is 150 kilopascal, then what is the mass of the car? Okay? So here basically we can find they gave us the pressure. We know that pressure is force over area. And they're looking for the mass. We know that the force is M times G, right? So they want the mass of the car. So what would my pressure be? Is my pressure 150 kilopascal? No, that's wrong. They said what? They said the pressure exerted by each tire is 150 kilopascal. That means the total pressure for 4 tires, it's going to be what? It's going to be 150. So it's going to be the total pressure, it's going to be 150 kilopascal, so 150,000 pascal times 4. Okay, it's equal to the force that we need to find over the area. What's the area? They gave us the total area, not the area of a single tire. No, they gave us the total area, which is 140 centimeter squared, right? Now remember, in physics we can't deal with non-SI units, so we need to change it from centimeter squared into what? Into meter squared. So basically, to go from centimeter to meter, you need to divide by 100. So if you're going from centimeter squared to meter squared, you need to also square the divided by 100. So you're dividing by 100 squared. So that means I get 140. And I should divide it by 100 squared. I got an answer of 0.014. So my actual area is 0.014 meter squared. Now how do I find the force? Force is equal to 150,000 times 4, because it's on the 4 tires, times the area, which is 0.014. Right? This is my force. So I got my force to be 8,400 newtons. Okay? So I'm looking actually for the mass. G, I'm going to assume it to be 9.8 because they didn't give it to me. So the mass is equal to the force over G. Okay, so what's the force? The force is 8,400 divided by 9.8. So I got my mass to be 857 almost kg. That's it for question 5. I'm going to turn off the mic and you're not going to see it for a while, because I low-key spammed it. So let's not spam it anymore. Okay, let's go back to the normal style. That's now question 6 grid. A steel box is fully submerged in water that its upper surface is 30 centimeters below the surface of water. So they gave us very valuable information. They said that we have like a place, we have a steel box that the top of the surface is 30 centimeters below water. So the depth of the steel box is what? It's 30 centimeters. But of course we can't deal with centimeters, so you need to divide it by 100, so 0.3 meters. What pressure does the water exert on the upper surface of the block? Okay, they didn't mention anything about the what's it called? The air pressure. Anyways, they're asking about the water pressure, so we don't really care about the air pressure. Okay, so you should know that the pressure of water is equal to what? Or not the pressure of water, just let's say the pressure of any liquid, okay? It's equal to the density of the liquid, okay? Multiplied by what? Multiplied by G, multiplied by the height that the object is submerged in the liquid. So in this scenario, the pressure of water that we're going to be dealing with, it's going to be equal to the density, the rho. What did I say here? It's density. I don't know what I called it before. The rho of water, which is 7, or not water. I don't know. Why did we choose 7,000? No, excuse me, this is the rho of steel. They put it here to trick us, and unfortunately I fell in the trick because I didn't read. Anyways, the density of water, which is 1000 kg per meter cubed, okay, times G, what's G? G is 9.8, right? Times the height submerged, which is what? Which is 0.30 meters. So you multiply them all together, you will get 2.94 kilopascal, okay? That's it for question 6. That's question 6. Now we'll move on to question 7. What does it say? In a hydraulic jack system, the small piston has a radius of 2.5 centimeters. So of course we need to change it to meters, so it's 2.5 times 10 to the minus 2 meters. And the large piston has a radius of 35 centimeters, which is 35 times 10 to the minus 2 meters. What is the magnitude of force that should be applied on the small piston to balance a 5,000 Newton force on the large piston? So basically, what you need to understand in this scenario is that the pressure exerted on the small system is equal to the pressure exerted on the large system. What does this mean? This means force of small over area of small is equal to force of large over area of large, right? So, they gave me the large force, which is 5,000 newtons, right? And then I have the radius, and I can find the area. The area is the area of a circle because it's a piston, right? So it's gonna be what? It's gonna be pi r squared. Okay, now for the other one, we're looking for its force. The area is also gonna be pi r squared. So pi r squared. Let me give this one the capital R because it's the bigger radius, okay? So look what happens. I can cancel pi and r and pi and r. Oh no, I can't cancel pi and r. I can cancel pi though. So pi and pi disappear. So now I'm left with this equation. The small force over the small radius squared is equal to the large force over the large radius squared. So I can do cross multiplication. I can get that the small force is equal to 5,000 times 2.5 times 10 to the power of minus 2 squared divided by 35 times 10 to the power of minus 2 squared. So put it on your calculator. 5,000 times 2.5 times 10 to the power of minus 2 squared divided by 35 times 10 to the power of minus 2 squared. I got an answer of what? I got an answer of approximately 25.5 newtons. So the small force is what? The small force is 25.5 newtons. So that's it for question number 7. We'll now move on to question 8. What does it say in question 8? They gave us a U-shaped tube is filled with water of density 1000 kg per meter cubed. That's shown in the figure below. In the left column of the tube, a quantity of oil was poured up to a height 125 centimeters. Once the oil is poured, the water level in the right column increases to a height 2. The tube is open to the atmosphere at both ends, so don't forget about the atmospheric pressure. Use G equals 9.8 meters per second squared and P initial to be 1.01 times 10 to the power of 5. They want the pressure at point B. Okay. So the pressure at point B, it would be what? It would be the pressure of water at the height 2, the pressure of water at height 2, plus the pressure of the air P0. So the pressure at B, it's equal to the pressure of the water, which is rho GH2, plus pressure of the air. So what is rho? Rho is 1000 times G, which is 9.8, times the height 2. Height 2, they gave it to us as 20 centimeters, so that's going to be 0.2 meters, plus pressure initial, which is 1.01 times 10 to the power of 5 pascal. So 1000 times 9.8 times 0.2 plus 1.01 times 10 to the power of 5. I got an approximate answer of 1.03 times 10 to the 5 pascal. So that's the pressure at point B. Now determine the density of oil. Very simply, you should know that the pressure of point B and the pressure of point A, because they are where? They are at the same level, it's going to be the exact same. This is something you should know, that 2 points at the same level, they have the same exact pressure. So pressure of A, it's 1.03 times 10 to the power of 5 pascal, okay? It's going to be equal to what? It's going to be equal to the pressure of the oil, which is going to be the density of the oil, multiplied by G, which is 9.8, times the height 1, which is the height of the oil, which is 25 centimeters, so 0.25, plus the pressure of the atmosphere, so 1.01 times 10 to the power of 5. So let's solve it. Just, you know what I'm going to do to get the most accurate answer? I'm going to keep the answer that I got over here, so that not this answer, I have the exact answer. I'll subtract from it 1.01 times 10 to the power of 5. I got 1960. So 1960 is equal to the density of oil times 9.8 times 0.25. Okay, so divide this by 9.8 times 0.25. You will get that the density of oil, it's 800 kg per meter cube. Now this makes sense. Why? Oil is less dense than water, so it floats on water, and this is the case. Oil is floating, Oil is floating on water. That's it for question 8. I'm not gonna do any top questions. Oh, why did I go all the way down? I'm not gonna do any top questions because we don't have any written part. I don't see a need to do the top questions. Anyways, we'll move on now to section 1.3, which is about buoyancy. So question 10 grid, what does it say? A solid sphere, okay, of radius 4 centimeters. Of course, we need to change it to meters, so that's going to be 0.04 meters, is fully submerged. This is the keyword, fully submerged, into a liquid of density 1020. So this is the density, kg per meter cubed. What is the magnitude of the upthrust acting on the sphere, given that g is 9.8 meters per second? Now, there's something you need to calculate the upthrust, to calculate the force upthrust, or the buoyant force, okay, it's gonna be what? It's gonna be rho, which is the density, times the volume submerged, times g. This is something very important to know. Since it is fully submerged, then I can use the full volume. If they said it's submerged 60%, I will calculate the volume, but then I'd need to multiply it by 60%. So you have to pay attention in the exam, okay? So rho, which is my density, it's going to be 1020 kg per meter cubed, times the volume submerged, which is the full volume of the sphere, which is 4/3 pi, times the radius, which is 0.04 cubed, times g, which is what? Which is 9.8. So you'll put it on the calculator and you will get an answer of 2.68 newtons, okay? That's it for question 10. We'll move on to question 11. It says define a buoyant force. Now, the buoyant force is something really important. It's the force that causes something to float or like stay in its position in the liquid, right? Basically, the buoyant force is the force exerted by a fluid on a body submerged in it. So, it's force exerted by a fluid on a body submerged in it, right? Now, there's actually another way to describe it and another way to calculate it, okay? It's like you have here, this is a tub of water, and then you have a block over here, right? Sorry for the deformed block. But then you have, at the top end, you have a pressure P1 or PI, and at the bottom end, you have a pressure PF. The difference in pressure, so delta P, which is P final minus P initial, okay? It's gonna be what? It's gonna be the buoyant, like, not really the buoyant force, but it results, here you go, here's what I'm looking for, it results in the buoyant force, okay? So now we'll move on to the rest of the question. A block of mass m, 650 grams, so 0.65 kg, is totally immersed, so you use the full volume, in a liquid of this density, so they gave us the density over here as shown below. The block is attached to a spring scale which indicates 5.25 newtons, so this is what? This is the buoyant force. Oh wait, actually that's not the buoyant force. It just has 5.25. They didn't mention the buoyant force. Let's just keep it at this, that it's not the buoyant force. Use G equals 10 meters per second squared. Now they asked us to calculate the buoyant force. Here, I can explain to you why this is not the buoyant force. Very simply, this is what the spring scale calculates once it's submerged in water. Whereas we can find the actual weight. So what's the spring scale actually like measuring? It's measuring the weight of the block. In water, the weight of the block reduces to 5.25 newton. Have you ever like tried, to carry something heavy and then you put it in water and it's like lighter, it's easier to carry? This is because of the buoyant force. So let's find the weight initial of the block. The weight initial of the block, it is 0.65 kg times 10, so that's going to be 6.5 newtons. We have the weight final, which is after it's submerged in water, so that's 5.25 newtons. Now, the buoyant force is the force that results in this decrease, so it's going to be weight initial minus weight final. So 6.5 minus 5.25, and that's going to be 1.25 newtons. Okay, that's it for part B. We'll move on to part C. They want the density of the block. I have, can I find the volume? No, wait. I mean, I could find it. I can't find the density of the block. Density equals mass over volume. I have the mass of the block initially, which is 0.65, right? I just need the volume. Okay, I can apply that the buoyant force, FB, or the upthrust force, it's the density of the liquid times the volume immersed, which is the full volume, times the G. So it's gonna be the density of the liquid, which is 1250, times V immersed times G, which is 10. It's equal to the buoyant force, which is what? Which is 1.25 newtons. So you solve for it, you will get that V immersed is equal to what? It's equal to 1.0 times 10 to the power of minus 4. So it's going to be 0.65 over 1.0 times 10 to the power of minus 4 meter cubed, and you will get 6,500 kg per meter cubed. Now, of course, it's more dense than the liquid. That's like, it makes sense that it's not gonna float, that it's gonna sink instead, okay? So that's it for question 11. We'll move on now to question 12, which is the last question of the chapter. Icebergs are huge, heavy bodies of ice floating in seawater. Given that the density of ice is about 900 kg per meter cubed and that of seawater is 1030 kg per meter cubed, what fraction of the iceberg is below seawater? Assume that the iceberg is floating in equilibrium in seawater. Do you want to know a cool fact? You know Titanic? Let me just draw a ship. This is not the Titanic ship, but let's assume this is the Titanic ship, right? And it was in the water here. And then we had like a huge iceberg. But this is like what the people saw. This was like the iceberg that they saw. Okay? They did not know that under it, there was something super huge. Because even though ice is less dense than seawater, it does not fully, float above the water. There's like a great part of it that goes underneath. So this tiny little seaboat, or like this tiny like ship, it hit and it crashed and it fell and it sunk. Imagine what would have happened if the full iceberg was on top. So like, imagine, wait, no, let me not erase these. Imagine now, here, this is my sea, and here's my boat. Imagine what would have happened. You know, that's like such a scary factor. Do you know the meme? I don't know if you've seen it, or like this thing on the internet where like you put like different levels on the iceberg. You have the tip of the iceberg and then you go all the way down, and like down is like the worst thing, or like the scariest thing. I don't know if you've seen it. I'll include it now. So here basically this is what I'm talking about. But anyways, that's enough yap for this question. They want us to assume that the iceberg is floating in equilibrium in seawater. They want us to find the fraction of the iceberg below seawater. Now, in equilibrium means not going up and down, because sometimes, of course, the iceberg goes up and down. It's not fully always at this point, but they're saying like just assume that it's not going up and down. Okay, so anyways, because it's floating in equilibrium, that means the weight of the iceberg is equal to what? It's equal to the buoyant force, right? Because it's floating in equilibrium, it's not moving up and down. So the weight is equal to the buoyant force. Like here, the weight is equal to the buoyant force, okay? Anyways, mg is equal to rho v immersed times g and g cancel. So you get that the mass of the iceberg is equal to rho of the liquid, because here this is the buoyant force equation, times the volume immersed. Anyways, here this is the mass of the iceberg. The mass of the iceberg is equal to the density of the iceberg times the volume of the iceberg, right? Which is the whole entire volume. So the mass of the iceberg, it's the density of the iceberg times the volume of the iceberg, which is the total volume, right? So then I get this equation. So then I can say that the volume immersed divided by the total volume of the iceberg, it's equal to what? It's equal to the density of the iceberg divided by the density of the liquid, okay, of the seawater. And of course they want the percentage, so we'll need to multiply it by 100. So to get the fraction that's actually floating, I'm going to take the density of the iceberg, which is 900, and divide it by the density of the seawater, and I'll multiply it by 100. So that's approximately 87% of the iceberg is submerged underwater, while only 13%, so this is what? This is underwater. Only 13% is above the water. So I'm just going to assume that it's going to look something like this, right? This would be our iceberg, something like this. And then you have this big thing all the way at the bottom. Okay? So that's it for question 12. Thank you guys for watching. This is chapter 1. So now we'll move on in the next video to chapter 2. Hello guys, and welcome back to chapter 2, mechanical waves and sound. So for chapter 2, we only have sections 2.1 until 2.5. I decided I'm not going to use the microphone anymore. It was fun only for the first part of the video, but now we actually need to focus. So let's get started with question 1. What does it say in question 1? Compare longitudinal wave and transverse wave. So when you're comparing these two waves, you have 3 types of comparison. You have, first of all, to compare their definitions. Okay. After that, you have to give 2 different examples. And then after that, you have to compare the particle motion. This is how you compare longitudinal waves and transverse waves. Okay, longitudinal waves, what is the definition of a longitudinal wave? It's a wave where the particle displacement is parallel to the direction of wave propagation. So we have the particle displacement, and then we have the wave propagation. Okay, for longitudinal, here, to fill in the gap, we say that the particle displacement is parallel to the wave propagation. For transverse, to fill in the gap, we say it is perpendicular. Okay? Now, some examples of transverse and longitudinal waves. An example of a longitudinal waves, it would be, for example, waves on a slinky. So if you got a slinky, which is like the string, you know, the toy string that you take and you move it up and down and whatever. But then an example of a transverse wave would be the waves on a string, right? Okay. Anyways, now we move on to the particle motion. What can we say about the particle motion when it comes to transverse waves and longitudinal? We know that the particle moves parallel in the longitudinal. So that means it does not move up and down, it moves back and forth. So the particle motion is back and forth in the longitudinal. For the transverse, it moves perpendicular. So for sure it's going to move what? It's going to move up and down. And that's it for question 1. Great, we'll now move on to question 2. They told us transverse and longitudinal waves are 2 types of mechanical waves. That's true. How do the particles of a slinky move when a transverse wave travels through the slinky? And how do they move with longitudinal? We just explained it up. Particles in the slinky, if there's a transverse wave, the particles, they move up and down. They move perpendicular to the direction of propagation. So it moves up and down. Or you can say that the particles move perpendicular, and then you cannot only say perpendicular, it's perpendicular to the direction of propagation of the waves. Now, when they say longitudinal wave, a longitudinal wave, it moves back and forth, right? So we know that the particles move back and forth. So that also means that they're moving what? They're moving parallel to the direction of propagation of the waves. That's it for part A. We'll now move on to part B. Very important question. Can these waves transfer matter and energy? No. As the wave propagates, it only transfers energy, not matter. A very famous example would be to take a rope. Take any rope you have, like a string, a thread, or whatever, and then take like a smaller rope, or like take a hair tie or whatever, and tie it, you know, like rip it and break it and then tie it. Or no need to break it, just like tie the hair tie on the rope. Then start moving your rope, right? You start moving your rope, and then you will see that your hair tie, it's moving what? It's moving up and down if you're using a regular rope. If you're using a slinky, for example, you might see that the hair tie is moving back and forth, right? But anyways, if you actually focus on the hair tie itself, at the end of like doing the whole wave process, you will see that the hair tie stays in the same exact position. That means matter is not transferred. So these waves, they can't transfer matter. However, they transfer energy. So in the exam, you say, as a wave propagates, it only transfers energy and not matter. Okay, we move on to question 3. Grid, what does it say? A transverse wave is traveling along a rope. The vertical displacement of the rope with the position x at a specific instant is shown below. Okay, they said, what is the displacement of the rope at position 24 centimeters? So this is 22, 24. The displacement is what? The displacement is minus 5. The y moves what? It moves minus 5. So you say the displacement is minus 5 centimeters, okay? At what position does the rope have 0 displacement? So you go over here. Which positions does the rope have 0 displacement? So here, this is 14 seconds. Or no, not 14 seconds, sorry, the position 14 centimeter. and over here this is 34 centimeter. So at positions 14 centimeter and 34 centimeter, the rope does not have any displacement, okay? Now, they're looking for the maximum displacement of the rope. Now, pay attention, in the exam, I don't know why they do this. They don't consider down to be the maximum displacement. The minimum displacement is 0. The maximum displacement would be at the top, like as much as it can displace. So it would be any points that touch here, right? That touch these two places. So basically, the maximum displacement would be at 4, at 24, and at 44. So these are all possible maximum displacements. In the exam, however, they choose always the positive one, like from +5, not -5. So it would be 4 and 44, okay? That's it for question 3 grid. We'll now move on to question 4 grid. What does it say? A wave is propagating on a stretched string that lies along the x-axis. A wave is propagating on a stretched string that lies along the x-axis. The displacement of a particle on a string at x equals 0.10 meters as a function of time is shown below. What are the displacements of the particle at time equals 0.2 seconds? So you go to 0.2 seconds, you will see that the displacement is 0. 0.5 seconds, it's 4. And 0.65, I'd assume this is it. So I get actually I kind of went off the track. Wait, 0.65 is here, so it might be here. I'm not sure what number I'm looking at. If it's -2.4, because the answer key says -2.8. So we're just gonna assume that it's -2.8. You have to get it like, I don't know, in half, so it would like somehow land here exactly, okay? So anyways, for 0.65, it's -2.8 centimeters. They said, does the horizontal position of the particle change? Justify your answer. Now, we said that the position of a particle is what? Is the transfer of, the change in position of the particle is the transfer of matter. But a wave does not transfer matter, it only transfers energy. So the horizontal position should not change since a wave transfers energy and not matter, okay? That's it for section 2.1. Now we'll move on to 2.2, which is the mathematical description of periodic waves. So they said, calculate the period of a wave whose frequency is 120 Hertz. Oh, excuse me. Oops. I just realized there's a part B I did not do. Okay, sketch the displacement versus position graph of the particles at x equals 0.10 meters for these for time equal to these positions. Basically, what you're gonna do, basically in the exam, what you're gonna do, is you're gonna go back to what you drew, okay, and then you will have kind of an idea, and you're gonna see 3 lines, okay. You're gonna see 1, 2, 3, and you have many different options, okay. So please choose the correct one, which is, for example, at 0.2 you'll choose this point here, alright. At 0.5 you'll choose this point here, and I don't know why they do this, but in the last position they oh, I flipped the waves. Yeah, in the last position the wave is usually flipped like this, and they put it here, okay. So just please remember this in the exam because it always comes, okay? Anyways, now we can move on to question 5. Calculate the period of a wave whose frequency is 120 Hertz. What is the relation between the period and the frequency? The period, it's equal to 1 over the frequency. So they want the period. It's going to be 1 over 120 Hertz. And anyways, you put it on the calculator. You will get 8.3 times 10 to the power of -3. And what's the unit of period? It's seconds. So anyways, 10 to the -3, we can change it, so it's 8.3 milliseconds. Okay, that's it for question 5. We'll now move on to question 6. What does it say? The period of a wave propagating along a taut rope is 2 milliseconds, and its wavelength is 30 centimeters. What is the speed of the wave? So question number 6, the period of a wave propagating along a taut rope is 2 milliseconds. So the period is 2 times 10 to the -3 seconds. And its wavelength is what? Its wavelength is 30 centimeters. So that's gonna be in meters. Of course, you need to change to the proper units. That's gonna be 0.3 meters. What is the speed of the wave? Okay, very simply, you should know that the speed of the wave, it's equal to what? It's equal to the wavelength times the frequency, right? And I know that my frequency is 1 over my period. Or I could say that I can say that my frequency is 1 over my period. So my speed, it's gonna be what? It's gonna be my wavelength times 1 over my period. So 0.3 times 1 over 2 times 10 to the power of minus 3. So it gave me 150 meters per second. That's it for question 6. We'll now move on to question 7. A wave traveling along a rope is described by this expression. So you should know the general format of this expression. It's yxt equals a, which is the amplitude, cosine, open brackets, you have kx minus omega t. So actually, before I continue, this is the displacement. So displacement, okay. This is the amplitude, okay. K is what? K is the wave number. Okay, X is what? X is the position. Omega is what? Omega is the angular frequency or the angular velocity. You should know this by now. So angular frequency. Okay. And yeah. T is what? T is the time. Now, how do I calculate my wave number and my angular frequency? Very simply, to calculate my wave number K, it's going to be 2 pi over lambda. Okay, my angular frequency, on the other hand, it's 2 pi. Actually, the angular frequency is denoted by omega, okay? It's actually 2 pi times my frequency. Okay, that's pretty much all you need to know. Part A, they said, what is the amplitude of the wave? The amplitude, you would look over here and you will find it to be 0.10 meters. Determine the wavelength of the wave. Very simply, how do I find the wavelength? I need to look at an equation that has wavelength. This equation over here has the wavelength because K is 2 pi over lambda. So I have my K, which is 25. 25 is equal to 2 pi over lambda. I'm looking for lambda. Lambda is equal to 2 pi over 25. So that's gonna be don't forget the units as well, rad per meter, right? And then this is also rad, so the rad and rad cancel. So then I'm gonna be left with what? I'm gonna be left with 0.25 meters, okay? That's it for part B. Now they want part C to find the period and frequency of the wave. If I find the frequency of my wave using this equation, then I will find the period as well, because the period is equal to 1 over the frequency. So omega is equal to 2 pi times f, right? So my omega, it's what? It's 9.4, right? Is it? Yeah, 9.4. And it's equal to 2 pi times my frequency. So my frequency, it would be equal to 1.5 hertz because I did 9.4 divided by 2 pi, okay? Now, how do I find my period? I'm going to do 1 over my frequency to get the period. So then I do 1 over 1.5, I will get 0.67 seconds. That is my period. Now, what is the wave speed? I have my frequency, I have my wavelength. How do I find the wave speed? Very simply, my wave speed is equal to my frequency times my wavelength, right? So it's gonna be what? It's gonna be, I got it to be 0.375 meters per second. Now, there's another equation for the speed that you could use, okay? It would be what? It would be omega, which is the angular frequency, divided by K, which is the wave number. Frequency divided by wave number, you get the speed, and they got 0.37 meters per second. Now, E, what does it say? Let me get rid of this. They said, what is the displacement of the rope at x equals 1.5 and the time is 2.35? So we just need to substitute them. So 0.10 times cosine 25 times x, which is 1.5, minus 9.4 times 2.35, close brackets. I got, now here actually we need to pay attention. Because we're dealing with rad, this is the main thing we're dealing with, and we have cosine. We need to change our calculator from degrees to radians. So I'm going to do shift mode 4 to change it to radians. So then I'm going to have 0.10 times cosine, then 25 times 1.5 minus 9.4 times 2.35. You put it on the calculator, and I got an answer of minus 0.095 meters, okay? Now, you return to normal by doing mode 1. Okay, that's it for part E. For part F, they said the general expression of the wave can be written as Very simply, you're gonna go back to what they gave you over here, which is 1.5 and 2.35, and then the general equation would be y 1.5, 2.35. So 1.5 meters, 2.35 seconds. That's it for question 7. Okay. Oh, sorry. There's more to this question. Yxt equals what, blah, blah, blah. They said where n is a positive integer and t is the period of the wave, find the displacements of the rope at x 1.5 and time 2.35 for n 1, 2, and 3. If n is 1, 2, and 3, okay, your time is going to be 2.35, and we found the period previously, it's 0.67. So every time you do it, you're going to get minus 0.095 approximately. So what does this mean? This means that the displacement of the rope at a specific position x and time t, it's equal to the rope's displacement for the same position x but different times. So the rope returns to the same vertical displacement after an integer multiple of period t. This is expected. Why? Because the wave is periodic, okay? So basically, again, you can write 1.5 meters, 2.35 seconds, okay? Anyways, we move on now to question 8. It says, what is the phase difference between two consecutive troughs of a transverse wave? Okay, you need to understand the concept of phase difference. Let me take this wave in the bottom. They said two consecutive troughs. So you have a trough here and a trough here. They want to find the phase difference. You should know. From one, you should know how to separate the waves, right? So you should know from here all the way to here, this is what? This is a whole 90 degrees. So all of this, right? It would be what? It would be 180 degrees. Then I add one more half, it would be 270 degrees. And then I add the final half, it would be 360 degrees. So if I am going from A, from this point over here, this is one half. Then I have 2 halves, 3 halves, 4 halves. That's from a trough to a trough, right? So that's going to be 90 plus 90 plus 90 plus 90. So all in all, it's going to be what? It's going to be 360 degrees. So this is the phase difference. So basically, in the exam, what you can do, you can separate them into halves, and you should know that each half is 90 degrees. Then if they say, for example, from point A to point B, this is how many halves? This is one half, right? Or like one section, okay, of my wave. So I will multiply 90 by 1, okay? If they gave me, for example, from here until here, let's count 1, 2, 3, 4, 5, 6. So that would be 90 times 6, and then I would get my answer, which is the phase difference. Okay. Now, another way you could calculate it is a very important way. To find the phase difference denoted by phi, you need to find the change in position, delta x over the wavelength. So delta x over the wavelength, and you'll multiply it by what? You'll multiply it by 360 degrees. So, for example, I started from here and I ended here, right? And let's say that each portion has a distance of like 1 meter, okay? So this moves 1 meter, 1 meter, 1 meter, and 1 meter. So delta x is what? Delta x is 4 meters, okay? Now, this is a whole entire what? A whole entire wave. So from here to here, this is what? This is the wavelength. And we have 1, 2, 3, 4. So 4 meters is the wavelength. So the displacement divided by my wavelength times 360 degrees will give me 360 degrees, which is what? Which is the phase difference. Okay, now we'll move on to question 9. What does it say? So what does it say in question 9? The diagram below shows the displacements y of particles on water waves as the function of distance x at a specific instant. So in part A, they want us to determine the wavelength of the water waves. So first of all, we have to know that the wave starts here and ends here, right? This is a whole complete wave, right? So this is one wave and this is another wave. So now in total, we have how many waves? We have 2 waves. And then we have what? We have not half a wave, we have a quarter of a wave. So this is 1, this is 2, this is what? This is not half, it's half of the half, it's a quarter, so it's going to be 0.25. So all in all, it's going to be what? The whole entire number of waves is how many? 2.25 waves, okay? And it spreads on a distance of 67.5 centimeters. So now, in order to get the wavelength, I'm going to do what? I'm going to take the total distance, which is 67.5 centimeters or 0.675 meters, divided by the number of waves, so I will get 0.30 meters. This is the wavelength of the water waves. Now, they want us to find the phase of points A and B. So point A, look here, this is 1/4, 2 quarters, 3 quarters, and 4 quarters. The whole entire wave is how many quarters? It's 4 quarters, okay? So, they want to find what? They want to find the phase of points A and B. So you can find it in two ways. You can either find it in degrees, or you could find it in radians. I prefer to do it in degrees. In the answer key, they did it in radians. Very simply, to change it from degrees to radians, there's like a simple conversion. So first thing, I'm gonna find it in degrees. First of all, for point A, it's 3 quarters, 3 over 4 of what? Of one wave, right? And one wave has what? One entire wave has a phase of 360 degrees. So 3 over 4 times 360 degrees. What's this gonna give you as an answer? You will get 270 degrees as an answer. You could do it like this, or instead of 360, you could put 2 pi if you want it in radians. So then it's gonna be what? Then it would be 3 pi over 2 in simplest form. This is for A. For B, on the other hand, B covers 4 out of 4, right? It covers like the full wave, so times 360. That means the phase is 360 degrees, or it is what? Or it is 2 pi, right? This is the phase of B. Now part C, they want the phase difference between points A and B using 2 methods. The first method you can do is you can find delta phi. It's equal to what? It's equal to phi of B minus phi of A, where phi is what? Phi is the phase. So delta phi, it's equal to what? It's equal to the phi of B, which is 2 pi, minus phi of A, which is 3 pi over 2. You will get pi over 2 radians. Or you could do 360 degrees minus 270 degrees to get 90 degrees. Now, another way of calculating it would be to find delta x divided by the wavelength and then multiplied by 360 degrees or by 2 pi. It does not matter, just either or. So let's see, what is the displacement from A to B? Now here's something very important to keep in mind. We know that one wave has a wavelength of how much? Of 0.30. So this is all in all 0.30. So I will separate it into 4 equal parts. So that's going to be 0.30 divided by 4, which is 0.075. That means this is 0.075, this is 0.075, this is 0.075, and this is 0.075, right? So from A to B, it moves how much? It moves a distance of 0.075. This is my delta x divided by the wavelength, which is 0.30 times 360 degrees or 2 pi. Okay, so you put it on your calculator. You will get an answer of 90 degrees. If you multiplied by 2 pi, you would get an answer of pi over 2 rad. So that's it for question number 9. Okay, we'll now move on to question number 10. It says a snapshot of a wave at a particular time is shown below. The snapshot shows the displacement y to a function of position x. They said the wave is progressive, having a speed of 340 meters per second. They want the wavelength of the wave, so you can choose any point. For example, you can start from here. Let's choose an accurate point. For example, from A over here, okay, from crest to crest, it's a wavelength, and from trough to trough, it's also a wavelength. So I could say from A, which is 0.2, until this point over here, which I'm going to call it x, it is what? It is 0.4. So the wavelength, it's going to be 0.4 minus 0.2, which is what? Which is 0.2 meters. Now, how do you calculate the frequency? You have the wavelength, you have the speed. Frequency is equal to speed over wavelength. So 340 over 0.2. So that's going to be 1,700 hertz, okay? Now, we'll move on to part C. It says, determine the phase difference between points A and B. So, look, here this is 1 quarter. This is the 2nd quarter. This is the 3rd quarter. And this is the 4th quarter. This plus this plus this plus this, all of them determine what? All of them determine the, they all make the wavelength. So you could do it like this, that this is 1 quarter, this is 2 quarters, this is 3, this is 4. So you can do how many quarters from A to B? That's 2, divided by 4 times 360 degrees, and you can get 180 degrees. Or you can do delta x over lambda times 360 degrees. So what's delta x? It's from 0.2 to 0.3. So that's 0.1, the difference. So 0.3 minus 0.2, 0.1, divided by the wavelength, which is 0.2 times 360, and you will get 180 degrees. That's it for question 10. We'll now move on to section 2.3, energy transfer in one-dimensional waves. It's gonna be, okay, what types of energy are associated with the propagation of a transverse wave along a rope? So we said only energy moves, like you have matter, it does not transfer on the rope, but only energy transfers. But we have 2 types of energy. Of course, we have kinetic energy, which causes the rope to move, and then we have the elastic potential energy, right? Energy. Oh my goodness, I forgot how to write energy. Energy, right? Which is always found in like ropes and pretty much everything that like, you know, like a slinky rope or a string, whatever, you know, it has elastic potential energy. And of course, there's also kinetic energy. Now we'll move on to section 2.4, sound wave. Okay, we start off with a question that does not give us sound, but it has the same concept as sound. Anyways, a light bulb of power 20 watts. They gave us the power, okay? Emits light in all directions. That means, here, you have to think about it in like a matter like this. Like, let's say here, this is the light bulb. It will emit light everywhere, everywhere, everywhere in the form of a sphere. Like, imagine you have a ball that lights up. You will see that the light it emits is all around it. It's like in the form of a sphere, not necessarily only a ball. Anything that lights up, it will emit everything out in a sphere. Okay. Modeling the bulb as a point source, what's the intensity of the radiation? 0.50. So this is the radius meters away from the bulb. Now they want the intensity. You know, intensity is power over area, and we said that anything will exert will emit whatever you're dealing with in the source of energy in a sphere. So the power is 20 watts over the area. What's the area? We know area, it's 4 pi r squared, right? So it's gonna be 20 watts over 4 times the 4 times pi times 0.5 squared. So you will get an answer of 6.4 watts per meter squared. That's it for question 12. We'll now move on to question 13. The intensity of a sound wave emitted by a loudspeaker is 40 milliwatts per meter squared. How will the detected intensity change if the amplitude of the sound produced by the loudspeaker? Okay, look, they gave us the intensity. It's what? It's 40 milliwatts per meter squared. It has a certain amplitude, we will call it A. Now, the relation you should know is that the intensity is directly proportional to the amplitude squared. If the amplitude decreases twofold, that means it halves. So that means you're going to half the amplitude by 2. That means if you square it, it will be amplitude over 4, so amplitude squared over 4. So that means I need to divide my intensity by 4. So they want us to find the new intensity. So it's going to be what? What's my intensity? 40. Right? Over 4, so it's gonna be what? It's gonna be 10 milliwatt per meter squared, okay? That's it for 13. We'll now move on to 14. So now question number 14, the intensity of sound waves at a distance of 5 meters from a source. So this is the radius and this is intensity 1. Okay, we know that they will have the same power, and power is equal to intensity times area, right? So it's going to be 0.15 times the area, which is 4 pi, times the radius squared, which is 5 squared. It's also equal to what? It's also equal to the second intensity 2 times the area, which is 2. 4 pi, and then the radius is 2 squared, so then 4 pi and 4 pi cancel, and then I get this equation. So then 0.15 times 5 squared over 2 squared is equal to intensity 2, right? So then intensity 2 is equal to what? It's equal to 0.94 watts per meter squared. That's it for question 14. Now we move on to section 2.5, which is question number 15. It is the Doppler effect. So let's talk about the general equation of the Doppler effect. It's very simply FO, which is the observer frequency. It's equal to Fs, which is the source, like the frequency of the source, multiplied by, please pay attention to this. You have V, which is the speed of sound in general, plus or minus, here I'll explain later, the velocity of the observer, over what? Over V minus plus the velocity of the source. So always remember that the sign on top, so whether you're dealing plus minus or minus plus, the sign on top means that it's moving towards, okay? Like it's moving to, for example, they're moving towards each other. A bus is moving towards a child, for example. And then the ones at the bottom mean that it's moving away. For example, the ambulance is moving away from the house, you know? So here, look what they said. An ambulance emitting a sound wave of frequency 900 Hz. So this is F of the source, 900 Hz. Is receding from a stationary observer. What does it mean, stationary observer? That means there's no velocity here. So times. They gave us the speed of sound of air, which is 340. Okay. It is receding from. That means it's going away from. So that's going to be what? That's going to be Actually, we don't care about the top because it's 0, so it's like this does not exist, okay? Divided by what? Divided by 340. We said it's going what? It's going away from, so we're gonna add what? The speed of the source, which is 25, okay? They want us to find the frequency, so it's gonna be 900 times 340 divided by 340 plus 25, so it's gonna be 838 hertz. Now, this is very important. You have to pay attention. You have here, this is the observer, and here you have the ambulance, right? The closer down, let's say the ambulance is moving like this. When it's moving like this, it's gonna squish these sound waves together, right? Because of this, what happens to the wavelength? It decreases. If the speed stays the same always, okay, then what will happen to the frequency if the wavelength decreases? It will increase, right? Because the frequency and the wavelength are inversely proportional. But now, here on the backhand side, look how spaced out they are from each other. So the wavelength, it increases, so then the frequency decreases, which makes sense. And look, this is the exact case. We know that the ambulance is going away from the observer, so it's going farther from the observer. So the wavelength, like the distance between each wave and the other one, will increase. So the wavelength increases, so then the frequency will decrease. And there you go, you see the frequency decreased from the original. Okay, now we'll move on to question 16. Now let's see. Again, what was the general equation? F observer is equal to the frequency of the source times, here you have the speed of sound plus minus the observer velocity, and the speed of sound minus plus the source velocity. Now remember, on top it's moving towards, on the bottom it's moving away from. We have an ambulance still moving in air with a speed of 20 meters per second, so this is the velocity of the source, the frequency of the whistle emitted by the ambulance, so this is F of the source, the speed of sound, this is V. If the ambulance is stationary, oh, okay, so they're saying that the speed of the ambulance is 0, so now Vs is equal to 0. Determine the wavelength of the emitted whistle. Now, they didn't give us the speed of the observer, so we're just going to assume that it's 0, okay? Like, we're standing still, and the ambulance is still. They want the wavelength of the emitted whistle, okay? We have what? We have the speed of sound in air, which is 340. Usually, we would add to it, or we divide it. Yeah, usually we'd add to it the speed of the source, but in this case it's 0, so we're not going to do anything. Divided by what? Divided by the frequency of the source, which is 500, so this will give us 0.68 meters. So that's it for part A. Now, here, this is very important. They're saying the wavelength of the whistle in front of the ambulance. So the ambulance is here, it's moving like this, and we have a person here, he's in front of the ambulance, he wants to hear the whistle. So that means the ambulance is going towards him. Remember, for towards, we always use the upper sign. So it's gonna be 500 times 340 plus V of the observer, which is 0, divided by 340 minus what? Minus 20. So you put it on your calculator, and we will get what? We will get actually the frequency of the observer. So what would that be? Actually, if I solve B, I'm also solving E at the same time, okay? So that's going to be what? That's going to be 500 times 340 divided by 340 minus 20. So I will get what? I will get 531 hertz. So for this one, it's 531 hertz. Now, I have the frequency. They want me to find the wavelength of the whistle. So what am I going to do? I'm going to take my answer, and then I have the speed of sound in air, which is 340. So 340 divided by my answer, which is 531 hertz. I get approximately 0.64 meters. This is the wavelength of the whistle in front of the ambulance. Now let's do it behind the ambulance. So if he was behind, that means he's moving away. Away, we use the lower sign, right? So that's going to be what? That's going to be 500 times 340 minus 0 divided by 340 plus 20. You will get what? You will get the frequency. So that's going to be 500 times 340 divided by 340 plus 20. So that gave me an answer of what? That gave me an answer of 472 hertz, right? Now, what do I do with this information? I can calculate the wavelength by doing the speed of sound 340 divided by the frequency. So 340 divided by 472, I got an answer which is approximately 0.72 meters. Okay, so that's it for question 16. That's it for this chapter. Thank you guys for watching. I hope you enjoyed and have a wonderful day. Hello guys, how are you today? I hope that everyone's doing well. So now I'm going to be explaining the chapter 3 light interference and diffraction. So for chapter 3 we have sections 3.1 until 3.4. So all in all I believe it is only 16 questions. Yeah, question 15, 16, that's the last question because like after 17 we go to 3.5. We don't have 3.5, we only have until 3.4. So without further ado, let's get started with the first question. Differentiate between electromagnetic waves and mechanical transverse waves, very simply. Now, electromagnetic waves, from its name, it's not a wave that propagates due to the transfer of vibration and motion between adjacent. No, it's not this. It's not the same as a mechanical wave, because the mechanical wave, it's what? It's a wave that propagates due to the transfer of vibration and motion between adjacent particles. So you have either particles moving perpendicular to the motion of the wave or parallel, right? So this is a mechanical wave. Whereas in the electromagnetic wave, an electromagnetic wave is transmitted through electric and magnetic fields. From its name, electromagnetic wave. So basically, it is what? A transverse wave. So first of all, you should know that electromagnetic waves are all transverse. So transverse, it is a transverse wave that moves or that is transmitted. This is a better way to say that is transmitted through oscillating. So I'm gonna write oscillating electric and magnetic fields, and you should know that they are what? They are perpendicular to each other, the electric and magnetic fields. Now, this is the definition, the difference in the definition. Another difference between electromagnetic and mechanical waves is that electromagnetic waves can propagate through regions where there is no material. So basically, they can move in what? They can move in vacuum, okay, when there is no matter at all. Okay, on top of that, actually no, there is nothing on top of that. Just that mechanical transverse waves, they cannot go in what? They cannot travel in vacuum, okay? So basically, in like short brief terms, mechanical transverse waves need matter in order for them to travel. Electromagnetic waves don't need matter. Why? Because they're transmitted oscillating electric and magnetic fields that are what? That are perpendicular to each other. Okay, that's it for question 1. We'll now move on to question 2 grid. It says the wavelength of a light wave propagating through vacuum is 650 nanometers. They want the frequency. So I have the wavelength lambda. I have the speed given by c in this equation, or you can write v, okay? They want to find the frequency. You should know that the frequency is equal to the speed of light over the wavelength. So it's going to be 3 times 10 to the power of 8 divided by what? Divided by the wavelength. Of course, you have to put it to the SI unit. So 650 times 10 to the minus 9. You put it on your calculator. I got an answer of 4.62 times 10 to the 14 hertz. Okay, so that's it for question 2. We'll now move on to question 3. Which part of the electromagnetic spectrum is visible to the human eye? Literally from its name, visible like light. So we have visible light, right? What about the visible light? From its name, it's visible to the human eye. They're asking for the approximate range. You should know that usually they say it's 400 nanometers to 750 nanometers, but here no, it's 375 nanometers, okay, to 750 nanometers, okay? We move on to question number 4. They said the electromagnetic spectrum consists of several regions that have different properties. So let me pull up the, okay, here we go. There we go. This is what I was looking for. Because you know how like sometimes it just comes up and we didn't even like prompt it to come up. Now, when we needed it, it took some time to pop up. But anyways, we brought it out. So for question 4, it's separated into 2 questions. Basically, what I'm gonna do is I'm gonna write for you the table and I will basically answer all of question 4 in one go. Okay, what I'm gonna do is I am gonna write first of all the name of the frequency. So the frequency name, okay, or like let's say the electromagnetic wave, the EMW, the electromagnetic wave name. Okay, this is the first separation in our table. The second separation would be a common use of it, and then the last separation would be what? It would be the wavelength range. Okay, so the very first thing we're gonna be starting with is the radio waves. So Again, the first thing we're starting with is the radio waves. Since we're starting with radio waves, let's talk about uses. From its name, radio waves, we use it in radio broadcasting and television broadcasting. So I'm gonna write TV or radio broadcasting. So this is a very infamous use of radio waves. Now, what is the wavelength range? Here you have to remember it, it's very important. It ranges from 1 millimeter, which is the smallest value, to 100,000 meters, which is the largest possible value. What comes after? I think I'll make it smaller. What comes after the radio waves? It comes the microwave. I still need to make it a bit smaller. Like this is fine. It comes the microwaves. What are some uses? Again, from its name, microwave. What do you do in the microwave? You heat your food. So one of the uses would be to heat food in the microwave. Another very important use is what is satellite communication. So we communicate with the satellite, or we have satellite communication by using microwaves. Now here, please pay attention to the wavelength range. It's 0.03 centimeters all the way up to 0.3 meters. Yes, there are intersections, but that is fine. It does not really matter. What comes after microwaves is the infrared, right? The infrared, here you have to if you know, for example, you know when you're driving on the highway and you go at very, very high speeds, right? And then all of a sudden you see there's a camera that takes a picture of you, and it will give you a fine if you go over the speed limit. How do they know that you're traveling at a really fast speed? It's very simply because of the infrared. Because the faster you move, the greater your infrared it's gonna emit more infrared, right? And because infrared has a certain wavelength, what it will do, what the camera does, is it sends it can measure the wavelength of it knows the wavelength of the infrared, and it can measure the frequency. That means how long does it take for one infrared wave to travel from it to you, from it to the car. So you will get the frequency, the frequency is how many waves are fit in the time it takes from the camera to your car, right? And so now it has the frequency and it has the wavelength, so it can calculate your speed. And if your speed is going above the limit, then for sure it will take a picture and it will give you a fine. You see, this is a very smart system, and how physics is used in daily life. Okay, so anyways, this is called thermal imaging, this process, thermal imaging. Okay, and another one, you can also use it for burglar alarm systems. Now, what is the range of the wavelength? The range is from 750 nanometers to 1 millimeter. Okay, now after infrared comes the visible light. I will just write VL. This means visible light. Very simply, visible light, you see a lot, you use visible light to see, so it's used in vision. On top of that, it's used in cameras. Okay, so the range, we just discussed it, it's 375 nanometers to 750 nanometers. Okay, now after that we have what? We have the ultraviolet UV. There's so many reasons we use ultraviolet. We use ultraviolet to sterilize water, so we call this water sterilization. Okay, and on top of that, we use it for what? We use it for security markings. We also use it for tanning. Security markings, when you put sunscreen and you see that it has a UV spectrum on it, this is because it will the sunscreen or the sun lotion will protect you from the harmful UV rays that come from the sun. So you can say water sterilization, security marking. You can also say tanning booths as well. Okay, anyways, what is the range? The range is 10 nanometers to 400 nanometers. Then what do we have? We have X-rays. This is very famous. You should know that it's used for what? It's used for medical imaging. You use X-rays if you break a bone. They're gonna imaging. Okay, yeah. You use X-rays when you break a bone so they can see how your bone looks like. They also use it in security systems. When you pass by the airport, they check what is in your luggage, what's in your bag, using X-rays as well. And then finally, last but not least, we have what? We have gamma rays. Now, gamma ray, oh wait, sorry, excuse me, I forgot to give the range here. This is 0.01 nanometer to 10 nanometers. And then finally, gamma, this is very important. It's used for cancer treatment. It's very, very important. It's cancer treatment, and not only treatment, but also detection. And then it's also used for imaging, basically like if you have like really big ships, imaging. If you have like really big ships or like a cargo, you can scan it using gamma rays, so you can detect what is in the crate, for example, or like what's in the ship, you know what I mean? And the range, it's gonna be what? It's gonna be less than 0.01 nanometers. So basically, this is what you need to know. What we notice is that as we go down the table, okay, what happens to the wavelength? The wavelength decreases. But what does this mean? This means that as we go down, what happens to our frequency? Because the wavelength and the frequency are inversely proportional to each other, then we'll say that the frequency will increase. So that was actually the first question, where they asked us to put the frequency bands based on increasing frequency. So it would be radio waves, then microwaves, then infrared, then then visible light, then ultraviolet, then X-rays, then gamma rays. Now they ask you which one is the fastest. Here you have to know. You are dealing with what? You're dealing with the same waves, electromagnetic waves, in the same space, in vacuum, right? In the same medium. They're gonna have what? They're gonna have the same speed no matter what, okay? So anyways, that's it for this question. I answered question 4. Oh, and sorry, they asked us to indicate which region travels fastest. They all travel at the same speed, right? But what speed do they travel in? In vacuum, they travel at the speed of light. In other materials, such as liquids, such as solids, they don't travel at the speed of light. This is not for us to discuss in this chapter. But if they gave it to you, like you have something in a liquid, and you have like an electromagnetic wave in a liquid, an electromagnetic wave in vacuum. Which one is faster? It's the one in vacuum. This is something you should know, okay? Anyways, we finished 3.1 and we'll now move on to 3.2, which talks about light polarization. Anyways, what is the definition of light polarization? And we also need to state what type of waves undergo light polarization. So basically, from its name, light polarization, you will take unpolarized light, okay, and you will turn it into what? You will turn it into polarized light. Now, what does this look like? For example, you have your waves, and your waves are always like traveling in all positions, okay? Then you have a polarizer over here. It has a slit like this. Then your wave will be traveling in one direction. Now, what type of waves undergo polarization? It's only the transverse waves that undergo polarization. Why? Because imagine you had a longitudinal wave and the particle is moving parallel to the displacement of the wave, right? Because of this, they're not moving in all directions. They're parallel. They're like this. They're moving like this, right? So it will pass by the slit undeviated, not bothered. It will continue like this. But if they were perpendicular to each other, for example, let's say it was like this and it was like this, then here, look what happens. It will come out and it will be like polarized, right? It will come out like constant, right? So basically, this is what you need to know for question 5. We'll now move on to question 6. We have a plane polarized light of intensity 1.6 milliwatt per meter squared is incident at a Polaroid film, whose transmission axis is at an angle of 30 degrees with the incident wave's plane of polarization. What is in milliwatts per meter squared the intensity of the transmitted light through the film? So here you have to pay attention to the key words, okay? The light is already polarized. If it was unpolarized, what would happen? Unpolarized. If it was unpolarized, no matter what the angle of the first polarizer was, if it was 90 degrees, 60 degrees, I don't know what, no matter what it is, the waves are gonna pass through, right? The light waves, the unpolarized light waves are gonna pass through and they're gonna come out polarized. But if this had an intensity of I0, then this would have an intensity of I0 over 2. So this I1 would be equal to what? It would be equal to I0 over 2. But then, if it passes through another one, and they said like, from this, the angle is 60 degrees, for example. Or not, let's not say 60, let's say theta degrees, right? Then now, look what happens. I will go to my previous intensity, which is I1. So I2 would be equal to I1 times what? Times cosine squared of my angle theta. Okay, so what do we understand from this? If my light was initially unpolarized, no matter the angle of my polarizer, like my film, right, it will come out half of my original intensity. But then, if it's polarized and it's passing through a film with a certain angle, but pay attention, the angle needs to be with the original, you know? So like this is the original, then here, this is my angle theta. I'm not taking the angle. For example, if they gave me, like, let's say this is my polarizer and this was the original one, and then they told me that this angle is 90 degrees. I don't take the angle to be 90 degrees. I take this angle over here, not the 90 degrees, this angle over here, which is the difference in the angles, like delta theta, between the new line of transmission and the old line of transmission, okay? And then your equation will be the previous intensity, not the original one, the previous intensity times cosine squared theta, okay? So anyways, look, we started with a polarized, it's initially polarized film, okay? And they gave us the intensity, which is 1.6 milliwatts per meter squared. It's incident at a Polaroid film, okay? So, whose transmission axis is at an angle of 30 degrees with the incident wave's plane of polarization. What is in milliwatt per meter squared the intensity of the transmitted light? So, I have my initial intensity. I know it's polarized. So, which equation am I using? I'm using I1 times cosine squared theta, right? They gave me theta. They want me to find I2. So, I2 would be equal to I1, which is 1.6. times cosine squared 30. So you put it on your calculator as cosine 30 squared, and I got an answer of 1.2 milliwatts per meter squared. That's it for question 6. We'll now move on to question 7. 3 analyzers X, Y, and Z are placed in front of an unpolarized beam of light as shown below. The transmission axis of an analyzer X is parallel to the y-axis. That of analyzer Y makes an angle theta with the y-axis, and that of analyzer Z here you go. They gave us the diagram below, and that of analyzer Z is parallel to the x-axis. The intensity of light emerging from the 3 analyzer system is 8%, the original intensity I0. So let's see what it says. Initially, we had unpolarized light. It passes through the first one, and then after it comes out from the 3 analyzer system, 8% of the original intensity. So here, this is I0, unpolarized light. It passes through here. Here it will have an intensity of I0 over 2. Then here, this was my initial plane of polarization. And then I turned it, and now I have a difference in angle being theta, right? So anyways, it will pass like this now. It will pass like this almost, right? Until it reaches here. And here, this new equation would be what? I'm going to call it I1. Here, I2, it would be equal to what? It would be equal to I1 times cosine squared times what? Times theta. And then it passes what? It passes through, and then it will emerge out like this. And then this one, which I will call it I3, it will be equal to the previous intensity, which is I2, times cosine squared theta. And we know it's equal to 8% of what? Of intensity initial. So now they're asking us, in which direction is the emerging light polarized? As you can see, the emerging light was polarized like this. So it's coming out, and we know that Z is parallel to the x-axis. So it's coming out from the slit of Z. So it's also going to be parallel to the x-axis. So it's basically moving in which direction? Along the x-axis. So it's polarized along the x-axis, okay? Now they want us to find the angle theta. So basically, what I can do is I can keep on substituting. So I0 is what? I0, okay? Then I1 is I0 over 2. I2, we said it's I1 times cosine squared theta. So it's going to be I0 over 2 times cosine squared theta, right? And then I3, we said it's I2 times cosine squared theta. So I3, it would be equal to what? It would be equal to I0 over 2 cosine squared theta. This is I2 times cosine squared the new theta. So I'm going to call this theta 2. But actually, we can find theta 2. Look, theta 2, if you drew it over here, you will see that it's perpendicular to the initial one. So all of this is 90 degrees. I'm looking for theta 2, which is this angle here, the difference between this one and this one. This one would then end up being 90 minus theta. So I'll multiply it by cosine squared 90 minus theta, okay? Okay, and I know I3, it's also equal to what? It's also equal to 8% of I0. So that's going to be 0.08 times I0. So let's solve it. I0 over 2 cosine squared theta times cosine squared 90 minus theta, right? Now here you have to pay attention. You need to know some rules from trigonometry. You should know that cosine theta, it's equal to what? It's equal to sine 90 minus theta. And similarly, sine theta is equal to cosine 90 minus theta. So if I square here, then I will also square here. So very simply, I could substitute this. I could rid of the 90 minus theta, and I will get sine squared theta, right? And this is equal to 0.08 I0, right? By the way, I0 and I0 cancel, so they can disappear. So now I'm left with cosine squared theta times sine squared theta. Now, another trigonometric property you should know is that 2 cosine theta sine theta is equal to what? It's equal to sine 2 theta. So look what I could do. I could take the squared out as a common, right? So then I'll end up with cosine times sine. So cosine, sine, so cosine theta sine theta, all of it being squared. Cosine theta, sine theta. I know 2 cosine theta, sine theta equals sine 2 theta. So cosine theta, sine theta, okay? It's equal to what? It's equal to sine 2 theta divided, so sine 2 theta divided by 2. So I could substitute this by what? By sine 2 theta divided by 2, and then I square it, right? So now, look what I have. I have sine 2 theta, all of it squared over 4, is equal to 1 over 2, sorry, not equal, sorry, times 1 over 2 because the I0 disappears. It's equal to 0.08 I0, or sorry, no, we also removed the I0. So now you move 2 times 4 to the other side. So now you have sine 2 theta, all of it squared is equal to 0.08 times 4 times 2, which is 8. So I got 0.64. You do radical on both sides. I have sine 2 theta is equal to 0.8. You do shift sine 0.8. I got, now please pay attention so that your calculator is in degrees and not in radians. So it's gonna be shift sine of 0.8, I got 53.1. I will divide it by 2. So now I have 2 theta is equal to 53.1. So I divide it by 2. I will get that theta to the nearest degree. It's 27 degrees. Okay. So all of this process, imagine all of this process in order to get what? In order to get the angle. Now they said, how can theta be varied to block all the light at the output of analyzer Z? Now this is a very important question. To block all the light out, I need to multiply something by 0. How could I possibly get 0? My intensity cannot be 0. So my intensity, we cannot change it. But we can change the angle theta. Try on your calculator. Cosine 0, you will get 1. Okay, that does not work. Cosine 45, you will get radical 2 over 2. That does not work. Cosine 90, you will get 0. So this is the key word, 90 degrees. What you need to do is you need to change the value of theta, okay, for it to be 90 degrees. So you need to rotate the analyzer by 90 degrees, okay. Now, they want to block it where? They want to block all of the light out of analyzer Z. So they don't want to send any light to analyzer Z. So what we should do in this scenario is, this is X and this is Y. We should turn Y 90 degrees perpendicular to X. So it would turn out to be like this, right? So then because of this, you will get theta to be 90 degrees, and then no light would pass through and it would not reach Z. This is all based on Malou's law. Okay, so that's it for question number 7. Question number 8, even though it is a top question, I will do it because I do believe it is necessary. So let's get started with question number 8. Explain why the term polarization does not apply to longitudinal waves. Now, diffraction and polarization, okay, are two different things. Diffraction, we'll discuss it next. So please do not say in your answer, oh, diffraction, that means it will diffract through. No, they're two different things. So please pay attention to what you need to say. Very simply, first of all, polarization only occurs in transverse waves. Why not longitudinal waves? Very simply, because the longitudinal waves, they oscillate, here's the keyword, they oscillate along the direction or perpendicular to the direction of the wave of propagation, no matter what the orientation of the slit is, right? So the waves will still be able to pass through. Okay, so again, we said because they are parallel to each other, the motion of the particles on the motion of the wave, because of this, they won't be able to get polarized. They will just pass through the slits, okay? So now we'll move on to part B. What does it say? A plane polarized has an intensity of 60 milliwatt per meter squared, right? And this is what? This is already polarized. It's not unpolarized, it's polarized. So we'll say P. It's incident on a Polaroid film whose transmission axis is at an angle of 25 degrees with the plane of light's polarization, so that does what, 25 degrees. Determine the intensity of the transmitted light. So here you need to apply that I1 is equal to I0 times cosine squared theta y, because it's already polarized, it's not unpolarized. So I1 is equal to what? It's equal to I0, which is 60 times cosine squared 25. You put it on the calculator. I got an approximate answer of 49.3 milliwatts per meter squared. Now, they said determine the ratio of the amplitude of the incident light to that of the transmitted light. Basically, my amplitude initial, it's directly proportional. No, the square of my initial amplitude, it's directly proportional to my intensity initial, right? And what does this mean? This means intensity 1 is directly proportional to amplitude 1 squared. So look what I can do. They were talking about what? They were talking about the ratio. So that means I'm going to do A0 over A1, right? So that's going to be, how am I going to get A0 and A1? I need to do radical for the both sides. So then I get here A1 is radical I1 and A0 is radical I0. So it's going to be radical I0 over radical I1, right? I can substitute I1 by what? By I0 times cosine squared theta, right? Now what can I do? I can combine the radical into one big radical because we have the radical up and down. So then I0 and I0 cancel, and now I'm left with A0 over A1 is equal to radical 1 over cosine squared theta, right? So now we can re-separate the radicals. So radical 1 and radical cosine squared theta. So you get A0 over A1 is equal to what? It's equal to 1 over cosine theta, because radical cosine squared theta is cosine theta. So anyways, A0 over A1, it's equal to 1 over cosine 25 degrees, which is going to be approximately 1.1. So that's it for question number 8. Okay. Now we have questions 9, 10, and 3.3. What did they say in question 9? In question 9, they said define the diffraction of waves. Now, diffraction of waves is very important. Pay attention to what I'm going to say. I'm not going to write it. The diffraction of waves is a phenomenon associated with what? With the spreading of waves. So what happens to the waves? It spreads. So spreading of the wave. So you're spreading the wave as they pass through. So they pass through a gap, or an edge, right? So again, the diffraction of waves is the spreading of a wave that passes through a gap or around an edge. Now, you have to pay attention. The wavelength, or the wave, okay, may only undergo diffraction when its wavelength has certain conditions. So the diffraction of a wave depends on the wavelength and certain conditions. So the wavelength, and we're gonna deal with what? We're gonna deal with the gap size. Okay, we're gonna call this gap size. Okay. Now, if the wavelength is equal to the gap size, then we're gonna have what? We're gonna have the most diffraction possible. So you're gonna have the most diffraction when the wavelength is equal to the gap size. If the wavelength is greater than the gap size, you will have still a greater wavelength, but it's less, greater diffraction, but it's less noticeable than if it were equal size. And then finally, last but not least, if my wavelength is smaller than the gap size, then there's going to be very little diffraction will occur. Okay, now we'll move on to question 10. What does it say? It says water waves in a ripple tank are incident on barrier with a gap. How will the diffraction pattern change when the gap gradually decreases? So the size of the gap will get smaller and smaller, but the waves stay the same. The wavelength stays the same. So the water waves will basically spread out more. They will diffract more. Why? Because now the wavelength, it's getting greater than the gap size, okay? Or it's almost gonna reach equal to the gap size. Okay? So basically what you can say is that the water waves will spread out more and more as the gap size decreases. That's it for question 10 in section 3.3. Now we have questions 11, 12, 13, 14, and 15, and 16, and that's it for chapter 3. Now let's go to question number 11. What does it say? Two sound waves of the same wavelength, which is 40 centimeters. So of course you need to change it to meters, so 0.4 meters, and the same amplitude of 1.2 millimeters, so 1.2 times 10 to the minus 3 meters, are incident at a certain point in space. What's the smallest path difference between these waves that will result in a constructive interference? Now, what in which conditions can we find the path difference if we're talking about constructive? In constructive interference, that's when you'll hear a loud sound. Basically, you're going to be achieving the maximum amplitude, okay? Here, you say that the waves, they are what? They are in phase. The waves are in phase. So their amplitudes will add up together. And usually, the equation for the path difference, which we'll call it delta L, in constructive interference, it's going to be n times lambda, where n is any number such as 1, 2, 3, even 0, 0, 1, 2, 3, 4, etc. So on and so forth. Okay? Now, they're asking for the smallest path difference. Of course, the smallest path difference, it's going to be what? It's going to be 0, okay? Now, pay attention. N cannot be negative. It's only, not positive. Sorry, I can't say positive because 0 is not positive. So not negative numbers, non-negative integers. Why? Because you can't take 1.5. You need to take 1, 2, 3, 4, etc. Okay? So, delta L for constructive is n times lambda, right? The smallest path difference would be if my n was 0, so it's going to be 0 times lambda, which is 0. So the smallest path difference, it's going to be 0. Now we'll move on to part B. They want the smallest path difference between these waves that will result in destructive. Now, what about the destructive interference? Basically, it's when you don't hear a sound. It's like a quiet sound that has minimum amplitude, right? Here we see that the waves are out of phase, right? So they cancel each other out. The path difference, delta L, in the destructive, it's going to be n plus 1 over 2 times lambda, where n is what? It's any number, like any non-negative number, any non-negative integer, such as 0, 1, 2, 3, etc. Okay, so the smallest path difference, it would be if you choose 0 as n, so it would be 0 plus 1 over 2, which is 1 over 2 times lambda. We know lambda is equal to 0.40 meters. Or basically 40 centimeters if I'm not mistaken. So it would be 1 over 2 times 40 centimeters, which is what? Which is 20 centimeters. So this is the smallest path difference of destructive interference, okay? We move on now to question 12. What does it say in question 12? Two loudspeakers, A and B, are placed 1.50 meters apart. So this is what? This is the distance. This is not delta L. This is just the distance, okay? We'll call this D. The loudspeakers produce in-phase sound waves of frequency 708 hertz. Now, you need to know that the speed of sound is what? The speed of sound in air or vacuum is 340 meters per second, okay? Actually, not vacuum. Sound cannot travel in vacuum. So only air, it would be 340 meters per second. Now, when I'm looking at delta L is the path difference. So usually, it's going to be the greater L, so L big minus L small. How do I find the L? L, it's the distance from the microphone or the source of the sound to where it's being emitted. Here, you see, always from the microphone or from where I'm sending the sound signal and to where it's released. So this is my L, the bigger L, and this is my L, the smaller L. How do I find the bigger L? This is making a right triangle, so I have to apply Pythagorean theorem. So it's radical 1.5 squared plus 1.2 squared, which you will get 1.92 meters. So delta L would be 1.92 minus 1.2, so it would be 0.72 meters. This is delta L. Now, they want to know, is it constructive or destructive interference? So basically, here we need to find n. We have delta L. Delta L is what? It's 0.72 meters, right? I know if it was constructive, it would be n times lambda. If it was destructive, it would be n plus half times lambda. So I'll just use this basic equation, the n times lambda, and I'll see the value of n. If it gives me a value of n that is, what's it called? A whole positive integer, then yes, for sure, it's going to be constructive. If it gives me a value of n that's number 0.5, then it's destructive, okay? But now, how do I find my wavelength? I have my frequency, they gave me my speed. My wavelength is equal to the speed over the frequency. So it's going to be 340 divided by 708, which is 0.48 meters. So now, delta L 0.72 is equal to n times lambda, which is 0.48. So n, you put it on the calculator, I got it to be 1.5. So because it's 1.5, I know what I know immediately. Because it's something 0.5, I know that it's what it is, destructive interference. Okay, that's it for question 12. We'll now move on to question 13. When are two light sources said to be coherent? There's only two conditions that they require from us. It is that, first of all, they have to have the same frequency. If they have the same frequency, then for sure they have the same wavelength. So the same frequency and the same wavelength. These two are considered one condition. On top of that, they must have a constant phase difference. Okay, that means always, no matter where you move throughout the difference, like throughout the two waves, you must always have a constant phase difference. So, thus, we can say what? Two light sources are said to be coherent if they have the same frequency and the same wavelength, and they have what? They have a constant phase difference. So, again, I'll repeat it for the last time. Two light sources are said to be coherent when they have the same frequency and, of course, the same wavelength, and the constant phase difference between the emitted waves. We'll move on now to question 14. In a double slit experiment, the wavelength of the frequency, of the laser light is 632 nanometers, so 632 times 10 to the power of minus 9 meters. The separation of the slits, so this is what? This is the small d separation of the slits. Okay, it's 1.50 times 10 to the minus 3 meters, okay? The slit to screen distance, all right, is 2.20 meters. This is the distance, capital D. What is the distance between two consecutive bright fringes? Now, before I proceed, you have to reread the question and you need to know, is it a single slit or is it a double slit? Here it's a double slit, so you need to pay attention. Whenever you have a double slit experiment, they might ask you for two things, either the bright fringes, the distance between the bright fringes, or the distance between the dark fringes, right? The distance between the bright fringes, it's what? It's n lambda. The dark fringes, it's n plus half times lambda. This would be what? This would be, if you're using, of course, n and lambda to find delta L, you know? But here, please pay attention. This is in what? This is in the double. In the single, it's so complicated to find the bright fringe, so that's why they're not asking us right now. In the single, excuse me, they will ask you only for the dark and you will use n lambda. The single, dark is the only excuse, or like the only exception for you to use n lambda in the dark. Otherwise, n lambda only belongs to the bright and n plus half belongs to the dark, okay? So here it's a double slit experiment and they're asking us for what? They're asking us for two consecutive bright fringes. Sorry, I chose the wrong color. Two consecutive bright fringes. So here you should know the equation. What's the equation? X equals m lambda capital D over what? Over small d. But please pay attention here. This is what I'm talking about, m. You know how for delta L we use n lambda, right? Here in this equation, they put, instead of n, they put what? They put m. So here, please pay attention. They are doing double slit, okay? For the double slit, what did they use? They used m lambda for the bright fringes. In the double slit, for the dark, it's m plus half lambda. But however, in the single, it's only gonna be m in the dark. For the bright, they're never gonna ask you. So they're asking us for what? They want the distance between two consecutive bright fringes. So this x is very, very important. Okay, two consecutive bright fringes. So that means, like, the difference between them is what? The difference between them is 1. Okay, because, for example, 2 minus 1, 3 minus 2, whatever you're gonna get, it's gonna be m2 minus m1. Like 100 minus 99, it's gonna be 1. That means my m is what? My m is 1. My lambda is 632, so that's 1 times 632 times 10 to the minus 9. Times my capital D, which is the slit to screen distance, 220, divided by small d, which is my separation of the slits, so it's 1.50 times 10 to the minus 3. You put it on your calculator, and I got 9.27 times 10 to the minus 4 meters. I'll leave always like the changing back into original units to you. So here, if you want to change it to millimeters, it will be 0.927 millimeters. Okay, that's it for question 14. We'll now move on to question 15. What does it say? In a double slit experiment, so please pay attention, double slit. The distance separating two narrow slits is 20.0 micrometers. So this is what? This is the small distance d. This small distance d is 20 times 10 to the minus 6 meters. The third order bright fringe, what does this mean? This means m is equal to 3. Is viewed on a wide screen at an angle of 4 degrees. So they gave us theta to be how much? To be 4.0 degrees. Okay, so now what are they saying in part A? They want to calculate the wavelength of the light source. You also need to know this equation. M lambda equals d sine theta. So they want to find lambda. Lambda is equal to d sine theta over m. D is 20 times 10 to the minus 6 times sine theta, which is sine 4. Divided by 3, I got 465 nanometers. Okay, that's it for part A. For part B, they said calculate Okay, so part B, calculate the total number of bright fringes viewed on the screen. It's a double slit, so they want the total number of bright fringes. What does this mean? This means the maximum value of theta, it's gonna be what? It's gonna be 90 degrees, okay? So what is the equation? We know x is equal to m lambda d over, or no, sorry, excuse me, it's the same equation we used here. M lambda equals d sine theta. They want the maximum number of m. M is equal to d sine theta over lambda, right? So sine 90, it's gonna be 1. So m is gonna be equal to d over lambda. So it's gonna be 4, no, what's d? D is 20 times 10 to the minus 6 divided by 465 times 10 to the power of minus 9. And you will get it to be what? You will get it to be 43. But, you have to remember, this, it's only 43 up, because remember, you have the central fringe, and then you have the 43 which is going up, and don't forget you also have the 43 that are going down. So 43 up, 43 down, and the center one as well. So that's going to be 86 plus 1. So in total, it's going to be 2 times 43 plus 1, which is what? Which is 87. So the total number of bright fringes viewed on the screen is 87. Now, part C, it says qualitatively describe how the interference pattern will change if a light source emitting a longer wavelength is used. So again, what is the equation? M lambda equals d sine theta. They said, I'm using what? I'm using a longer wavelength. So my wavelength increased. My d stays the same, okay? So what will happen to my angle? My angle is going to increase. This is due to the proportionality, because they're on opposite sides of the equation, okay? So my lambda increased, okay? So my theta is going to increase. So what happens? I can say that the maxima and the minima will spread out, okay? And then because of this, what will happen to my m? My m will decrease. So I'll have a smaller total number of fringes on the screen. The only thing that doesn't change is d, because d is a constant, okay? So that's it for part C of question 15. And now, last but not least, our final question. What does it say? To determine the wavelength of a light beam, a group of students set up a double slit interference experiment. These slits are 0.030 millimeters apart on the screen, 0.50 meters away from the slits, as shown below. A monochromatic coherent light source is placed. What did they say? The sixth bright fringe from the screen is 5 centimeters away from the central fringe, not counting the central bright fringe. So here, this is, for example, the sixth bright fringe. We have here what? We have here the distance from the spacing, like the distance between the slits and the screen, so 0.50 meters. And here they give it to us as what? As 5 centimeters, so 0.05 meters, right? Now, they want the angle between the sixth fringe and the horizontal, so they want this angle over here. I have opposite, I have adjacent. I can do tangent theta is equal to the opposite 0.05 over the adjacent 0.5. So then I do tangent inverse. I will get theta to be 5.7 degrees, okay? Now they want us to calculate the wavelength of the light source. I have what? First of all, the equation, I have x equals m lambda capital D over small d. I have capital D. I have x, which is 0.05. I have the small d, which is the separation of the slits. I have m, which is 6. I need to find lambda, so it's doable. Let's do it. So I'm going to move everything to the other side. So x times d over m times capital D is equal to lambda. So 0.05 times d, which is 0.03 times 10 to the power of minus 3, divided by what? Divided by m, which is 6 times capital D, which is 0.50, you put it on your calculator, so 0.05 times 0.03 times 10 to the power of minus 3 divided by 6 times 0.5. I got an answer of 5 times 10 to the minus 7, so basically 500 nanometers. This method works, but it's not accurate. The more accurate method would be to use the angle, so you do m lambda equals d sine theta. So then I want to find lambda, so d sine theta over m is equal to lambda. So 0.03 times 10 to the power of minus 3 times sine 5.7 divided by m, which is 6. So you put it on your calculator and you will get 497 nanometers, which is the more accurate one. So in the exam, I advise to do both methods, and then the more accurate one, you choose it. Okay, now that's it for part B. We'll move on to part C. It says determine the distance separating the two consecutive bright fringes. This is a double slit experiment. They want the distance, so they want x, separating two consecutive bright fringes. So I'm going to be using m. So x is equal to m, and what's m? 2 consecutive bright fringes. That means, for example, 2 and 1, so the difference between them is 1, times what? Times lambda, which we found to be 497 times 10 to the power of minus 9, times the separation, which is 0.50, like not the separation, the distance from the slits to the screen, divided now by the separation, which is 0.030 times 10 to the power of minus 3. You put it on your calculator, and I got an answer of 8.3 millimeters. That's it for part D. Now finally, last but not least, for part C. Now finally, last but not least, for part D, how does changing the distance between the slits affect the spread of the bright fringes? So pay attention. Here, we need to use the equation x, because they're talking about the spread. X is equal to m lambda capital D over small d. They said changing the distance between the slits. So let's say they decrease this, right? And let's say that lambda is constant and d is constant, okay? The only two things that will change are x and m. So as d decreases, because it's inversely proportional to x, because x directly proportional to 1 over d, so it's inversely proportional. That means x is gonna increase, right? But because d, it's on the same side as m, but it is under it, right? It's not like on the numerator with it, it's on the denominator, then we can say that m, if you move, for example, d to this side, you will get that m is directly proportional to what? It's directly proportional to d. That means if d decreases, then m decreases. So basically, if I made the slits closer together, they will have a greater distance between the fringes, so the pattern will spread out, okay? So the number of fringes will decrease, okay? Now let's say I did the opposite. Let's say I increase this, so my x would decrease. So the spacing between the fringes decreases, so they compress together, and the number of my m's will increase. That's it. That is pretty much it for question number 16. That is it in total for chapter 3. So thank you guys for watching. I hope you enjoyed and have a wonderful day. See you in the next chapter. Hello guys, welcome back to the next chapter. So this is chapter 5, current, resistance and electromotive force. So from chapter 5, this is in the electricity and magnetism course question documents. We have from sections 5.1 to 5.4. So these are going to be from question 1 until question 13, because I don't do the top questions. So basically it's from 1 until 13. Okay, so without further ado, let's get started with the very first question. A 5 coulomb, this is what? This is the Q, the charge of charge, flows in a circuit every minute. So the time is how many? Always your time needs to be in seconds. It's 60 seconds, okay? They want us to find what? They want us to find the current I in this circuit. Very simply, you have to remember the equation. What is the equation? It's very simply the current, it's equal to the charge divided by the time. So I is equal to Q over T. So the current I is equal to 5 coulombs divided by 60 seconds, which is 83 milliamperes. Okay, so that's it for question 1. We'll now move on to question 2. The mean drift velocity. So this is what they gave us, if you continue reading until here. This is the drift velocity, which we will call it Vd, okay? In a wire of cross-sectional area, so they gave us what? They gave us the area, A, okay? The electron number density. What is the electron number density? The electron number density is N, okay? Now they're saying, what is in amperes the current of this wire if they gave us Q to be 1.6 times 10 to the minus 6? Now again, you need to know this equation. I is equal to N, which is the electron number density, times A, which is the surface area, times V, D, which is the drift velocity, times what? Times Q, which is Q, okay? So now let's look again and let's change everything to the proper units. The only thing that we need to change the units is this one. So 0.11 millimeters per second. How do I change it into meters per second? Very simply, I need to divide by 1000, right? So it's going to be 0.11 times 10 to the power of minus 3 meters per second. So now what do we do in order to find the current I in amperes? We need to substitute. I is equal to N. What did they give us N as? They give it to us as 5.86 times 10 to the 28 per meter cubed, okay? We'll multiply it by the area, which they gave it to us as 2.0 times 10 to the power of minus 6 meters squared, okay? Then we'll multiply it by the drift velocity, which we found to be 0.11 times 10 to the minus 3 meters per second. And then we'll multiply it by Q, which is 1.6 times 10 to the power of minus 16 coulomb. So again, 5.86 times 10 to the 28 times 2.0 times 10 to the minus 6 times 0.11 times 10 to the minus 3 times 1.6 times 10 to the minus 16, I got an answer of what? I got an answer of, oh, excuse me, it's not 16, it's 19, my bad. So anyways, you put it on the calculator and you should get an answer of 2.06 amperes, and that's it for question 2. We'll now move on to question 3. What does it say? A thick copper cable in a car's electrical system is 1.2 meters long. This is the length. And has a diameter of 5 millimeters. That means the radius is 2.5 times 10 to the minus 3 meters. How did I know? Very simply, it's in millimeters, so I multiplied by 10 to the minus 3. So my diameter is 5 times 10 to the minus 3. I need the radius, I divided by 2 to get 2.5 times 10 to the minus 3. When the car is starting, we have a current. So this is the current I flows through the cable. The number density of free electrons is this. So this is what? This is N. Okay, they want us to calculate the current density in the cable. Okay, the current density J. Okay, current density denoted by J. It's equal to what? It's equal to, from its name, current density. It's basically the current divided by the area. It means how much current is concentrated in each area, like in the part of the area. So it's the current divided by the area. This is the current density. So it's going to be 150 amperes divided by the area. What's the area? Because it's a cable, okay, the cable is what? It's a wire, right? If you cut it, if you look at the surface area, you will see it to be like this, a circle, right? And what's the area of a circle? It's pi r squared. So it's going to be what? It's going to be pi times 2.5 times 10 to the minus 3 squared. So what would be the current density? It would be 150 divided by pi times 2.5 times 10 to the minus 3 squared. You put it on your calculator. And the two significant figures, I got it to be 7.6 times 10 to the power of 1, 2, 3, 4, 5, and 6. So times 10 to the power of 6. And what's the unit? It's the ampere divided by the meter squared, okay? Because it's the current divided by the area. Now, what are they asking in part B? They're asking to find the drift velocity of the free electrons, okay? Now, what's the equation? I equals N times A times VD times Q, right? I'm looking for the drift velocity. So the drift velocity is equal to what? It's equal to I over N times A times Q, right? But now, here's something very important. We determined that I over A, it's what? It's the current density. So I can remove I over A, right? And I can substitute it by the current density. So then I will get that the drift velocity is equal to the current density divided by N times Q, right? So it would be 7.6 times 10 to the 6 divided by 8.5 times 10 to the 28, right? Times times Q. Now here, this is important. Q always needs to be an absolute value here because we're dealing with an electron. Q is what? Q is 1.6 times 10 to the minus 19 coulomb, right? So it's going to be 8.5 times 10 to the 28 times the absolute value of this, which is what? Which is 1.6 times 10 to the power of minus 9. Right, so you put it on your calculator and I got an answer of 5.6 times 10 to the power of minus 4 meters per second. This is the drift velocity. Now what are they saying in part C? Estimate the time it takes an average electron to travel the full length of the cable. Now here, this is basic physics. You have the velocity, you want to find the time, and you have what? So this is VD, right? You have the distance, which is the length of the cable, which is 1.2 meters. You want to find the time. So very simply, time is equal to the distance over the drift velocity. So it's going to be 1.2 over 5.6 times 10 to the minus 4. You put it on your calculator. You get 2.1 times 10 to the power of 3 seconds. And if you divide it by 60, you will get almost 35 minutes. So that's it for question 3. We'll now move on to question 4, which is in section 5.2 in Ohm's law. Now, the resistivity of a certain metal is this. So this is what? The resistivity that we denote it now in physics by rho. Let's say rho initial, because it's initially rho initial. At this is temperature initial. It's temperature coefficient. This is what? This is the temperature coefficient that we denote by alpha. They want us to find rho final given temperature final. Now there is an equation you need to know. Please memorize it. It's very important. It's what? It's rho final is equal to rho initial times 1 plus alpha times the change in the temperature. Okay, so we're looking for rho final. Rho final is equal to rho initial, which is 2.30 times 10 to the minus 7 times 1 plus the alpha, which is 0.0600 times the change in temperature, which is 35 minus 20, which is going to be 15. Okay, so you put it on your calculator. 2.3 times 10 to the minus 7 times, open brackets, please pay attention to your brackets, 1 plus 0.0600 times 15. You put it. Oh, excuse me, here I forgot a 0. Here, this is very important. Please don't do this mistake. Don't forget the 0. Look how many zeros there are here. I forgot to put them here, so please pay attention, okay? So you put it on the calculator, and I got to three significant figures, 2.51 times 10 to the minus 7, and the unit is ohm times meter. So that's it for question 4 and section 5.2. Now we'll move on to section 5.3. Question 5, they said that the potential difference across a circuit element is 12 volts. So this is the voltage. When a circuit of 0.30 amperes, this is the current, right, flows through it, they want what? They want the resistance of the element. What's this question? They want the resistance. You know that the resistance is equal to the voltage divided by the current. So it's going to be 12 divided by 0.30, which is what? Which is 40 ohms, okay? That's it for 5. We'll now move on to 6. 6 is very important. It says sketch the IV characteristics for a metallic conductor and for a filament lamp and for a diode. Now, a metallic conductor is the same as an ohms conductor. You have to know, for example, always they will put what? They will put for you what type of graph they want you to draw. They want you to draw the IV graph. Now, you have to pay attention. If they said VI graph, then you need to do the opposite of what you did here, okay? So the metallic conductor is an ohms conductor, so it will follow the resistivity rule, like the resistance rule. So it's a straight line passing through its origin. Ignore this curve at the end, okay? This is a metallic conductor, so I will call this MC. This is the metallic conductor. FL, the filament lamp, okay? Again, this is I, and this is what? And this is V, okay? They're looking for what? They're looking for the IV characteristics of a filament lamp. Now, please pay attention. The IV of a filament lamp, it looks like an S. Okay, so look, for example, here it's increasing, then all of a sudden it starts curving like this. It starts curving downwards. Then here it's decreasing, then all of a sudden it starts curving upwards. So this is the graph of an IV filament lamp. Okay, and now finally, last but not least, the diode. Now, what you need to know about the diode, okay, so this is the diode D. This is I, this is V. The diode, in the negative parts, it doesn't work. And then it comes at some point here in the positive part. It's also not working. And then all of a sudden, it has a sudden increase. This is the graph, the IV graph of a diode. Now, what I'm going to do is I'm going to put a display of all of the required graphs. So let me just pull it up. Okay, so here this is an example of what you need to pay attention to. Here, pay attention, it's the VI graphs, not the IV graphs. The IV graph would be the inverse. So the fixed resistor, which would be an ohmic conductor, or a metallic conductor, which is a fixed resistor, it's a straight line passing through the origin. Here, the filament in the VI, we said it's flipped. So it's not going to be S, it's going to be SZ, the opposite of the S. Now, a semiconductor diode looks somewhat like this in the VI, okay? Now pay attention, in the VI the thermistor looks like an S, but in the IV graph, okay, let's say you're dealing with an IV graph, okay, then the thermistor will look like a Z, so it would be the opposite, it would look something like this, right? Now that's pretty much most of what you need to know. In addition, add the diode that they drew over here, so excuse me, 1 second. So in addition to this, add the diode that was drawn over here, and that's it for question 6. We'll now move on to question number 7. It says state Ohm's law. Ohm's law is basically the definition of a resistance. Okay, it's basically any electric component for which the ratio of potential difference across it and the current through it is constant obeys Ohm's law. So I'm gonna write it. Let me just write. So again, any electric component for which the ratio of potential difference to current across it is across it or through it is constant, then it will obey what? It will obey Ohm's law. Basically, V over I, if it, for example, if R is always constant, for example, if V is 2 and I is, let's say, 1, and then suddenly V is 4 and then I is 2, my resistor, or my resistance, it's always going to be 2. So my resistance is constant. So you say that this is what? This is an ohmic conductor. Why? Because the resistance, which is the ratio of potential difference to current, is constant, so it obeys Ohm's law, so it's an ohmic conductor, okay? Anyways, that's it for 7. We'll move on now to question 8. What does it say? Question 8, what does it say? Calculate the resistance. So they want us to find R. When they gave us the length, so the length is 3 meters, they gave us the cross-sectional area. Now, we cannot keep it in millimeters squared. So from millimeter to meter, what do? We do times 10 to the minus 3, right? So millimeters squared to meters squared, I'm going to do times 10 to the minus 3 and I squared. So basically times 10 to the minus 6, right? So it's going to be 1 times 10 to the minus 6 meter squared. And then they gave us the resistivity rho. They want to find the resistance. Now, here's another equation you should know. Resistance is equal to resistivity times length over area. This is something very, 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 very important you need to know. So we're looking for resistance. Resistance is equal to the resistivity, which is 1.69 times 10 to the minus 8 times the length. the length is 3 divided by the area, which is what? Which is 1 times 10 to the minus 6. You put it on your calculator and you should get an answer of 5.1 times 10 to the minus 2 Okay, that's it for question number 8. We'll now move on to question number 9. What does it say? It says, describe how an increase in temperature affects the resistance of a PTC, positive temperature coefficient, and NTC, a negative temperature coefficient. Now here, this is logically speaking a positive temperature coefficient. That means the more temperature I have, like the higher temperature I have, the greater the resistance it's gonna be. So as my temperature increases, this in the PTC, as my temperature increases, my resistance increases. Now for the NTC, it's the opposite. As my temperature increases, what happens to my resistance? It will decrease, okay? That's it for question 9. We'll move on to question 10. What does it say? A 2.10 volt battery. So this is what? This is the voltage. Potential difference is maintained across a 2 meters. This is the length of tungsten wire of resistivity 5.60 times 10. So this is the resistivity. They gave us the cross-sectional area. So it's 0.500 times 10 to the minus 6. You should know the conversion by now. They want us to find the current in the wire. I can find the resistance and I have the voltage, so I will be able to find the current. First of all, resistance is equal to what? Resistivity times length over area. Then current is equal to voltage over resistance. That's it very simply. So resistance is equal to my resistivity, which is 5.60 times 10 to the power of minus 8 times the length, which is 2 divided by the cross-sectional area, which is 0.500 times 10 to the power of minus 6. So what is my resistance? Very simply 5.6 times 10 to the minus 8 times 2 over 0.500 times 10 to the minus 6. This is an answer that will be 0.224. This is what? This is the resistance. So then my current is 2.10 divided by 0.224, right? So it gave me the correct significant figures, 9.38 amperes. This is the current in the wire. We'll now move on to question number 11. It says, consider a light-dependent resistor exposed to intense light. So from its name, a light-dependent resistor, the greater amount of light I have, right, the less resistance I would have, okay? So here's something you need to know, that the intensity of light is inversely proportional is inversely proportional to what is inversely proportional to the resistance. This is an LDR. So if I am exposed to more intense light, right, the intensity of light increases. What will happen to my resistance? My resistance will decrease, so my resistance drops. What happens to the current? Okay, let's assume the voltage remains constant, okay? If my resistance drop, I know that my voltage is equal to my current times my resistance, right? My voltage is constant. My resistance drop, what will happen to my current? My current will need to increase. So as the intensity of light increases, my current will also increase. So that's it for question number 11. We'll now move on to question number 12. What does it say? A battery of EMF 12 watts. So this is the EMF. Okay, has an internal resistance. So this is small r, 1.0 ohm. So they're looking what? They're looking for the terminal potential difference, which we will denote by VAB across this battery. When a 20 ohm, this is the big resistance resistor, is connected to it, okay? So what is the main equation that you need to know? You should know that VAB, which is what? Which is the terminal potential difference. It's the EMF, okay? Let me write EMF like this. This is the EMF minus what? Minus I times small r. So what I have, first of all, I need to find VAB. I have the EMF, I have small r, I need to find I. It's gonna be I total, okay? So I total, it's what in this case? It's gonna be the EMF, the voltage, which is 12, divided by the total resistance, which is 20 plus 1. So this resistance plus this resistance, you add all the resistances, and then you do voltage divided by the resistances, you will get 0.57 amperes. So this is what? This is my my current. So now VAB is equal to EMF, which is 12, minus the current, which is 0.57 times 1. So you put it on the calculator and you will get it to be almost 11 volts, okay? More specifically, it's 11.43 volts, okay? This is the terminal potential difference. That's it for question 12. We'll now move on to question 13, and we're done for this chapter, okay? What does it say in question 13? In the circuit below, we have E1. This is the cell 1. It's 14 volts, right? Let me just write it here. We have small internal resistance 1, it's 3 ohms, right? we have E2. E2 is what? E2 is 10 volts, and we have small internal resistance 2 to be 2 ohm, and we have the resistor R to be out what? It's 5 ohms, right? Now they're looking for what? They're looking for the current. We know that the current in this thing, it's gonna be I total. I total is what? It's the total voltage divided by the total resistance. So let's find the total voltage. Total voltage is what? First of all, I have 14. Let's take the positive sense to be like this, okay? Let's say this is the positive sense for my voltage. So it's flowing from the positive end to the negative end. So first of all, it's gonna be plus 14. Then here you come and you see that it's entering from the negative into the positive. So pay attention, pay attention. We're starting from a positive and it's flowing and it enters what? It enters a negative one. So from positive to negative, this is what? They are not put opposite to each other. They are put together in series. I want to say, yeah, so the cells are put together in series. So thus I can add them together. So it's going to be plus 14 volts plus what? Plus 10 volts. So the total voltage is what? It's 24 watts. Okay. Now the total resistance, I just add it all together. It's 2 plus 3 plus 5. So anyways, it's going to be 24 volts divided by 10, which is what? Which is 2.4 amperes. That is the current. Now they want to find the VAB of point A relative to B. So VAB. Now here, this is very important. VAB, first of all, it's the terminal voltage for this cell over here, right? It's gonna be what? It's EMF minus I times small r. But which EMF? The EMF of the cell itself, which is 14, minus the current, which is the current always, which is 2.4, times the small resistance, which is 3. So you put it on your calculator, you will get 6.80 watts, okay? Now find the potential difference VDC. So VDC of point D relative to point C. Now here, again, VDC, we're always going from like the positive end to the negative. You see DC, here, AB, right? So again, it's going to be EMF minus IR. But which EMF? Now the EMF of the cell itself, which is 10, minus the current, which we know to be 2.4 times the small internal resistance of the cell, which is 2. You put it on the calculator and you should get 5.2 volts. And that's it for this chapter. Thank you guys for watching. I hope you enjoyed and have a wonderful day. See you in the next chapter. Hello guys, how are you? And welcome back to the next chapter, which is chapter 6 DC circuits. In section 6.1, we're going to be analyzing, before we continue, in chapter 6 we have 6.1 until 6.4, okay? So it's only from questions 1 till 12. I'm not going to be doing the top questions, which is question 13 and onwards, okay? Anyways, we'll move on to section 6.1. What does it say in question 1? Consider the circuit in the figure below. Calculate the current. They want to find I in the circuit and the terminal voltage VAB, okay, across the source of EMF, okay, and the potential difference between points A and B. Okay, so here we cannot call this VAB. We'll just say that they want the terminal voltage. Why? Because this here is VAB, but this VAB is not the terminal voltage, it's something else. Why do we say VAB? I say VAB because it's easier to associate it with something. So here in this scenario, VAB is something else. It's not the terminal voltage. Anyways, let's start with what they want. Initially, they want the current. I in this current, because it's a single loop, the I, it's gonna be 1I. So I total is equal to V total over what? Over R total. So it's gonna be what? What's the total voltage? The total voltage in this is 9, okay, divided by the sum of resistances, which is 1, plus 1.5 plus 0.5. You put it on your calculator, so that's 9, right? Divided by 1 plus 1.5 plus 1, all in all, that's gonna be 3 amperes. So my current is what? My current is 3 amperes, okay? Now they want the terminal voltage. The terminal voltage in our case, of course, we're going to take it from the positive end to the negative end. So it's going to be the voltage from C to A. Now, you know the terminal voltage, or as we say, VAB, or in this case, VCA, it's the EMF minus I times the internal resistance. The EMF is 9 minus the current, which we found to be 3 times the internal resistance, which is 0.5. You put it on the calculator and you will get 7.5 volts. That's the terminal voltage. Now they want the potential difference between A and B. So here is A and here is B, right? Now here what we can do is we can find the potential difference very simply. We have the resistance and we have the current. So resistance times current is going to give me the voltage to be 3 volts, right? But here this is something very important. You need to look at where your current is flowing. The current goes from the positive end all the way to the negative end. So from B to A, how is it? It is from B to A, the potential difference is what? It's plus 3 volts. So VBA is plus 3 volts. Let's say in the exam they ask you to find VAB. Now, your current, it's flowing how? It's gonna be flowing in the opposite direction than how to VAB is flowing, right? This is the direction of your current. Let me use a different color. This is the direction of your current, right? And AB is in this, so they're in opposite directions. That means VAB is gonna be minus 3 volts. So that's it for question 1A. Now B, they want us to sketch a graph to show the potential drops and rises around the circuit. They said assume the wires do not produce any resistance. So basically, I'm gonna keep this graph here and I'm gonna draw what they're talking about over here. It's not gonna be accurate, it's just like an estimate, okay? Anyways, let's start at point A. At point A, we're starting over here. It does not have any potential difference, right? But then what happens? It passes through it passes from A to C through the battery in the direction of the current. That means it's gonna increase all the way to the top, right? Because what happens, it gains potential difference, right? It gains potential energy. Then because of the internal resistance, because it's a real cell, it will drop. Because there's internal resistance, it will drop. By how much will it drop? Let's say, for example, here, this is what the potential difference being 9 volts, okay? But we found the terminal voltage. Do you remember we calculated the terminal voltage V, CA? Do you remember? We calculated it. Why? Because it's from here to here, between the cell, right? And we found it to be what? We found it to be 7.5 volts. So that means it's gonna drop all the way to where? All the way to 7.5 volts, okay? Then, what do we have after this? We have a wire, of course. Then, what happens after the wire? It will drop again from C to this point over here. It will drop, but then this point, we are gonna say it has the same voltage as B. That means it will drop all the way from C to which point? To point B. Now, what's the voltage of B? Very simply, it's gonna be the current, which is 3 times 1.5. What's 3 times 1.5? It's gonna be 4.5. So we know at this point over here it's 4.5, and at this point over here it's what? We found it to be 7.5. So what's 7.5 minus 4.5? The difference, it's gonna be what? It's gonna be 3. That means this drops all the way to 3 volts, right? And then this over here is 3 volts, and this will cause a drop of how much? Of 4.5 volts, okay? Now, anyways, we have what? Over here we have 3 volts, and then this will cause a drop of what? Of 3 volts, so I'll end up with 0 at A again. So it will fall again, like this, all the way until it reaches A, and then it will continue like this. So this is an estimate of what your graph should look like. Please, please, please pay attention. Try to understand your graph. Try to understand what you're dealing with. Try to understand that this point has 0, then it passes through here, and then it gains. Then here, because of the resistor, it will drop, and then it will stay constant here because there's nothing, and then it will drop again here. So, you have to understand the graph you're dealing with in order to be able to sketch, okay? Anyways, that's it for question 1. We'll move on now to question 2. What does it say? The potential difference across a 20 ohm heating element is 120 volts. So this is what? This is the resistance, and they gave me the potential difference V. They want to find the power. Now we know that power is equal to the current times the voltage. If I don't have the current, I can replace it by voltage over resistance. So power is equal to voltage over resistance times voltage. So it's voltage squared over resistance. So 120 squared divided by 20. So that's going to be 720 watts. That's it for question 2. We'll now move on to question 3. What does it say? A light bulb of electric power. So they gave us the power of the light bulb. It's 100 watts, okay? It's operating under a voltage of 220 volts. Now this is what? This is my voltage. They want to calculate the current. We know that P is equal to I times V. So I is equal to P over V. So it's equal to 100 over 220, which is what? Which is 0.45 amperes, okay? Now, they're saying calculate the electrical energy consumed by the light bulb in 2 hours. Now, we know that power, it's equal to work over time. Work in this case is the energy that they're talking about. That means my power times my time, it's going to give me the energy, which is my work. So, 100 times the time. They said in 2 hours. So, 2 hours times 60 minutes times 60 seconds. You always change it to your SI units. I got 7.2 times 10 to the power of 5 joules. That's it for question 3. We'll now move on to question 4. What does it say? A 10 ohm resistor carries a 0.50 ampere current, right? So this is the resistance. This is my current. Calculate the power dissipated and the energy consumed. So first of all, we know power is I times V. If I don't have V, I can substitute it by IR. So then power is I times IR. So it's I squared R, right? So it's going to be what? It's going to be 0.50 squared times 10, which is what? Which is 2.5 watts. This is my power. Now they want the energy consumed in 20 minutes. We know that energy over time is equal to power. That means energy is equal to power times time. That means it's 2.5 watts times what? Times the 20 minutes, but of course you need it in SI units, so you will multiply it by 60 seconds. So 2.5 times 20 minutes times 60 seconds, I got 3,000 joules. Okay, that's it for question 4. We'll now move on to question 5. What does it say in question 5? For the circuit shown below, find the rate of conversion of chemical energy into electrical energy, as well as the power output of this. Now, pay attention. When they say the rate of conversion here, they're talking about the power, okay? The power, right, that's needed to change chemical energy into what? Into electrical energy. What is changing chemical energy into electrical energy? You should know this. The cell. The cell is changing chemical energy into electrical energy. So we need to think and we need to look at the power dissipated by what? By the cell. So here now in the case power, we know it's I times V. How do I find I? I can find the current I because here it's a single loop. I total is equal to the voltage 4.5 divided by the sum of resistances. So 0.5 plus 0.5 plus 2. All in all, I got 1.5 amperes. Now I can find the power. It's 1.5 amperes times what? Times the voltage, which is 4.5 volts. This will give me 6.75 watts. That's the rate of conversion of chemical. Now they want the power output of the cell. Now here this is different. The power, the rate of conversion of chemical energy is this power over here, okay? We'll call this the power input, P input, okay? P in, okay? Minus what? Minus I squared times R, okay? That means this is what? This is the dissipated, okay, dissipated heat, okay? It will give me what? It will give me the power output. So you have to think of it logically. What I calculated, I said it's the power dissipated, but no, I'm wrong. It's the power that was inputted, which is the rate of conversion of chemical energy into electrical energy. This power input, it's always I times V, right? So I had my I to be what? I found, sorry, the power input, it's 6.75 watts. Now, the heat dissipated, it's always, it doesn't have anything to do with the voltage because the voltage is different across each component. But here in this scenario, it's always, because it's a single loop and the current is the same everywhere, it's always the current squared multiplied by the resistance. So here, what's my current? My current is 1.5, so it's going to be 1.5 squared times my resistance, which is 0.50. You put it on the calculator to get the power output. So I got my power output to be 5.63 watts. Okay, so that's it for question number 5. We'll now move on to question number 6. What does it say? A car battery is being charged. Oh, here, this is very important. A car battery is being charged. It's not charging something else. It is being charged, right? So it's not charging, it is being charged. Now, if it was charging something, then if they asked us to find the terminal voltage, VAB, we would find it by doing what? By doing EMF minus I times R. But this is if it's charging something else. So charging something else, you use this equation. Now it's being charged, so it's gaining the charge, right? So now VAB, it's gonna be what? It's gonna be EMF, not minus, but plus IR. Okay, so I have my current, which is 15 amperes. I have the EMF to be 10.5, and we have the internal resistance. They want the terminal voltage. VAB is equal to 10.5 plus 15 times 0.08, so I got 11.7 volts. That's it for A. For B, they want the power dissipated inside the battery. Now, remember what we said in question 5. The power dissipated, how do we calculate it? Because it's a single loop, it's always the current squared multiplied by the internal resistance, or like multiplied by the resistance. So 15 squared times 0.08, that's going to be what? That's going to be 18 watts. Now here, the power input to the battery is always calculated by doing the current multiplied by the voltage. So what's my current? It's 15. And what's my voltage? It's what? It is, here pay attention, it's the terminal voltage, which is 11.7. So times 11.7 watts. I will get what? I will get 176 watts. Now there is another way to do it. You can say that the power input, okay, it's equal to what? The total power. It's equal to EMF times I, okay? In addition to what? In addition to I squared times the internal resistance. So here it would be what? It would be 10.5 times 15 plus 15 squared times 0.08, and you would also get 176 watts, okay? That's it for question number 6. We'll now move on to question number 7. What does it say? Consider the circuit below, okay? They want us to calculate the current in the circuit. First of all, I need to see which one has the higher EMF, 3 versus 6, this one. So this is the main one we're going to be focusing on. The 6, if you continue it, okay, you will see that the positive end reaches the positive end. So they're placed opposite to each other. If the cells are opposite to each other, then we subtract them. That means the total EMF in this case, it's not 6 and it's not 3. It's 6 minus 3, which is what? Which is 3.0 volts, okay? Is this what they're asking for? No, they're asking for the circuit, the current in the circuit. The current I, which is one loop, so it's going to be the total current. It's going to be the voltage or the EMF, which is like the net voltage or the EMF, which is 3.0 volt, divided by the total resistance, which is 1.5 plus 2 plus 0.3 plus 0.2. All in all, I got 0.75 amperes. Now, the rate of energy conversion from electric to chemical. This is basically, they're asking for the power input. How do you calculate the power input? It's always going to be the current multiplied by the voltage, or in this case, the EMF, okay? So the net voltage or the EMF. So it's 0.75 times EMF, which is 3. So I will get 2.25 watts, okay? So now, they want the power output of the energy source to the circuit. Where is the energy source? This is the energy source. This is the energy sink. We don't care about it, and they don't want the net, okay? So they want the power output. Remember, the power output is equal to the power input minus the heat dissipated. This means that the heat dissipated, okay? So my power input, it's always what? It's always I times EMF. What's my current? My current is 0.75 times my EMF of my source, which is 6. 6. Minus the heat dissipated, which is always I squared times the internal resistance. I squared is 0.75 squared multiplied by the internal resistance. What's the internal resistance? It is 0.3. You put it on your calculator and you should get an answer of 4.33 watts. Okay, that's it for part A. Now, what does it say in part B? It says, suppose that the 6 voltage source of EMF is removed and reinserted with the reverse polarity. So we flipped it now. This is positive, this is negative, this is positive, this is negative, right? They're saying what would become of the current in the circuit. So let's see what happens. Let's calculate the total EMF. This is my positive, it goes all the way to the negative, so they're not placed opposite, they're placed adjacent and in the same direction, so you can add the EMFs together. So my EMF is equal to 9 volts. So now, my current is going to be the EMF, which is 9 divided by 0.3 plus 0.2 plus 2 plus 1.5. So it's going to be 2.25 amperes. Okay. Now, what is then the total rate of electric energy dissipated? So I have my current. Okay. I have, okay, they want the total rate of electric energy, not anything specific. So it's always I squared times R. But which R here? It's going to be the R total, all of the resistances. So it's going to be 2.25 squared times 0.30 plus 0.20 plus 2 plus 1.5. All in all, it's going to be what? It's going to be 20.25 watts. That's it for question number 7. We'll now move on to section 6.4, questions 8, 9, 10, 11, and 12, and we're done for this chapter. What does it say in question 8? 3 resistors of resistances 15, 5, and X ohm are connected in series. Now, when resistors are in series, you add them all together. So you have resistor like this, resistor like this, resistor like this. You have R1, R2, R3. Resistance total is equal to R1 plus R2 plus R3. Okay? Okay, if they were in parallel, so then let's say it's like this, then like this, then you have another one like this. Okay, so this is R1, R2, and R3. R total, 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So, because they're in series, we can add them together. So 15 plus 5 plus X is equal to 50. So then X is equal to what? You need to solve it. You will get that it is 30. Now for question 9, 3 resistors of resistances 80, 20, and 10 are connected in parallel. So total resistance, 1 over total resistance is 1 over 80 plus 1 over 20 plus 1 over 10. I got it to be 13 over 80 ohm. But this is 1 over total resistance. Total resistance, you need to flip your answer. And I got what? I got 80 over 13 ohm. So that's it for 9. We'll move on now to 10. What does it say? Okay, we have 3 resistors of resistance 100, 220, and 470. It's connected in series across a 24-volt battery. They want the current in each resistor and the potential drop across each. So because they're all in series, then the current for them, it's going to be the same. That means I1 equals I2 equals I3 equals I total. And that's equal to V total over R total. So it's equal to 24 divided by 100 plus 220 plus 470. So that's going to be 30.4 milliamperes, okay? Now they want the potential drop against, or the potential drop across each. How do you find it? You'll just multiply the current by each resistor. So for this one, the potential drop, it's 30.4 times what? Times, oh wait, but don't forget, because this is in milliamperes, so 30.4 times 10 to the minus 3 times 100, you will get it to be 3.04 volts. Here then, 30.4 times 10 to the minus 3 times 220, you will get this to be 6.69 volts almost. And then 30.4 times 10 to the minus 3 times 470, I got this to be 14.3 volts. Okay, so that's it for question A. Now we'll move on to B. How does the power dissipated in the 100 ohm compare to that in the 470 resistor? Now remember, how do you calculate power dissipated? It's I squared times the resistance. So, anyways, for the 100 ohm, the power dissipated, it's gonna be 30.4 times 10 to the minus 3, all of it squared, okay? So please put your brackets as well so you don't get the wrong answer. Multiplied by what? Multiplied by the resistance, which is 100. So I got what? I got 0.092416. Okay. Then, if I did the same exact thing, 30.4 times 10 to the minus 3 squared times what? Times 470, I will get 0.4343552. So this is power 1, power 2. If I did power 2 divided by power 1, I will get that, let's see on the calculator, 0.4343552, or no, 553, divided by 0.092416. So it's almost 4.7. That means power 2 is equal to 4.7 times power 1. That means the power of the 470 is equal to 4.7 times the power of the 100. Okay, that's it for part B. We'll now move on to C. What does it say? Calculate the total power dissipated in the resistors. The total power dissipated in the resistors, it's gonna be what? It's gonna be the current squared multiplied by the total resistance. So it's gonna be 30.4 times 10 to the power of minus 3, all of it squared, times 100 plus 220 plus 470. All in all, I got 0.73 watts. This was the power dissipated in the resistors. We'll now move on to question 11. What does it say? Two resistors of resistance 4 kilowatts, so 4 times 10 to the, 4 kilo ohm, so 4 times 10 to the 3 ohm, and 6 times 10 to the 3 ohm are connected in parallel. So what is the total resistance? It would be 1 over 4 times 10 to the 3 plus 1 over 6 times 10 to the 3, right? So 1 over 4 times 10 to the power of 3 plus 1 over 6 times 10 to the power of 3. And then whatever answer you get, you need to do 1 over the answer, because this is what? This is 1 over total resistance. So anyways, after solving, I got my total resistance to be 2,400 ohms. Okay, they gave us what? They gave us the potential difference, or the voltage. They want us to find the equivalent resistance. We found it already. It's 2,400 ohms. They want the total current. The total current, I total, is equal to the total voltage divided by the total resistance. So 12 divided by 2,400, so that's 5.0 milliamperes. They want the current through each, and they want the current through each resistor. So I have what? My current here. Okay, this is the total current. I have my potential difference. In parallel, the potential difference does not split. In parallel, the potential difference is the same. Okay, so the current across each, that means it's gonna be, let's say I for, let me call this 1 and 2. I for resistor 1, it's equal to 12 divided by 4 times 10 to the 3, right? So that's 3 milliamperes. And then I2, it's going to be 12 divided by 6 times 10 to the power of 3, so that's going to be 2 milliamperes. And if you add them together, it will give you the total resistance, which is 5 milliamperes. And now finally, last but not least, they want the total power dissipated in both resistors. Now, remember, how do you calculate the total power dissipated in both resistors? It's always I squared times the R, and because it's in both resistors, it's going to be R total. So it's going to be 5 milliamperes squared, so 5 times 10 to the minus 3 squared times what? Times the total resistance, which we found it to be 2400 ohms. So all in all, I got 60 milliwatts or 0.06 watts. Okay, that's it for question 11. Now finally, the last and final question, which is question 12. It says consider the circuit below. They gave us R1 as 4 ohms, R2 is 12 ohms, and R3 is 10 ohms, and the small resistance is 0.20 ohms. They want us to calculate the current through each resistor. Okay, so how do you calculate the current through each resistor? First of all, I need to find the total resistance. So total resistance is equal to what? First of all, these two are in parallel. So to get them, it's going to be 1 over 12 plus 1 over 4, and then I do 1 over the answer, right? So I will get what? I will get 3 ohms as an answer. Okay, so that's 3 ohms, and now the rest are all in series, so you can add them. So 3 plus 10 plus 0.2, that's going to be 13.2 ohms. Okay, now we can find the total I total, it's equal to what? It's equal to the total voltage, the EMF, which is 3, divided by the total resistance, which is 13.2, so you'll get 0.23 amperes. But this is not the resistance across each one. Or sorry, this is not the current through each resistor. This is actually the current here, and the total current here. Here the current will split up later, but they don't want us to talk about it. In the answer key, they said it's fine. You can say that this and this and this, all of them have the same current, which is what? Which is this one. Now they want the potential drop. That means they want the voltage across each resistor. Let's start with the equivalent resistance. Here, let's say this doesn't exist anymore. This goes bye-bye. And they substituted it with what? They substituted with resistor 1, 2. So this is the equivalent resistance of resistor 1, 2. So they want the potential drop, V equals IR. So you do it for all of them. First of all, V12, it's equal to what? It's equal to 0.23 times the equivalent resistance, which is what? Which is 3. So that's going to be what? That's going to be 0.69 watts. Then V3, it's equal to what? It's equal to 0.23 times 10. So that's going to be 2.3 volts. And then the V4, this is V4. Or no, small r, V small r, it's equal to what? It's equal to 0.23 times 0.2. So that's going to be what? That's going to be 0.046 watts, okay? Anyways, we know here that the I for resistance 3, we found it to be 0.23 amperes. And it's the same for the I of what? It's the same for the I of the small internal resistor. And this is equal to the I of 1, 2. But now they want us to find the current of each resistor. Now, what we did is very important. We found the EMF of 1 and 2. Because they are in parallel, they have the same EMF. That means over here, this is what? This is 0.69 and this is 0.69, right? I have this resistor here, which is how much? Which is 12. And I have this one to be 4. So I can now find it. So I1, it's equal to what? It's equal to V1 over R1. So 0.69 divided by 4, so that's 0.17 amperes. And then I2, it's equal to 0.69 divided by 12, which is 0.058 amperes. And if you add these two together, you will get what? You will get 0.23 amperes, okay? That's it for part A. We'll now move on to part B. What does it say? It says calculate the current in the EMF source and the terminal voltage across it. So, I think I already calculated the EMF and the, did I? Actually, no, the EMF is given to us, it's given to us as 3. And here you should know, because this is in series with the rest of the circuit, that the current in the EMF source, it's the same as everything else, which is 0.23 amperes. Now they want to find the terminal voltage, VAB. VAB is equal to the EMF minus IR. So it's going to be 3 minus 0.23 times the internal resistance, which was what? Which was 0.2. So you will get 2.95 volts. That's it for this chapter. Thank you guys for watching. I hope you enjoyed, and see you in the next and final chapter for part A. So thank you guys. See you. Hello guys, how are you? So now this is the last and final chapter for the AS Physics full revision for part A, which is chapter 1 Nuclear Physics. We have sections 1.1, 1.2 and 1.3. So that's going to be from question 1 until question 17, okay? So without further ado, let's get started with the first question. It says, describe the composition of an atom based on Rutherford's model. I have a separate video explaining the whole entirety of chapter 1. I'll try to include it in one of I'll include it in the AS Physics playlist. I think it's there, let me check. So yes, I did explain it, and I explained also the course practice with it. So if you open the AS Physics playlist and you go to the very last video that I had. But anyways, so if you want to understand what I'm talking about, you need to open that chapter, okay, to get all of the necessary important notes. Anyways, let's continue with the question. Describe the composition of an atom based on Rutherford's model. According to Rutherford's model of the atom, what does he say? He says we have in the nucleus charged particles that are positive, so they are charged protons, and then we have particles that don't have a charge, which are neutral neutrons. Okay, they make up what? They make up the nucleus of the atom. We call these nucleons. And then all around we have what? We have orbiting around the nucleus in a cloud, we have the electrons. This is the structure. So how do you say in the exam? You say that he said that in the nucleus there are charged protons and neutral neutrons, whereas the electrons move around the nucleus in a cloud. That's it for question 1. Now for question 2, it says, what did Thomson's atomic model propose about the structure of the atom? Now Thomson, on the other hand, he said that the atom was a sphere that is like positively charged, okay, and then it has electrons, like negatively charged electrons, embedded within the sphere of positive charge. Okay, this is Thomson's model. So again, Rutherford's model, you have a nucleus, the nucleus has positive protons and neutral neutrons, and then that orbit around it in the electron clouds are the electrons. Thomson, on the other hand, he said you have just a sphere of positive charge that has inside of it what? The negatively charged electrons. Okay, so that's it for question number 2. We'll move on now to question number 3. It says, consider the following electrically neutral nuclei. They want the number of protons. So when you have X, A, Z, you should know that Z is the number of protons. Okay, A is the number of nucleons, which is what? Which is neutrons plus protons. Okay, and X is of course the element. So how many protons does it contain? It contains 26 protons. How many neutrons does it contain? It's going to be the number of nucleons, 56, minus the number of protons, which is 26. You will get 30 neutrons. How many electrons? Here's the keyword. It's a neutral. That means the number of electrons is equal to the number of protons. That means it does not have a charge. So the number of electrons will be 26 because it's the same as the number of protons. We'll now move on to question number 4. It says 2 nucleotides are isotopes of the same element. What is the definition of an isotope? It's basically they are atoms of the same element that have the same proton number but different mass number, which is the different nucleon number. So we can say that their proton number is the same, so they will have the exact same proton number. You don't change the proton number, but what changes is the nucleon number, more specifically the number of neutrons. So you can have either more or less neutrons, which will affect the nucleon number. Okay, we'll move on now to question number 5. Oh, before, let me explain more. If the protons stay the same, that means the chemical reactivity does not have, like, it's not changed for the protons. But since the nucleon changed, then the physical state, or like the physical reactivity or the physical properties of the nucleus or of the isotope will change. Okay, so the proton number will affect the chemical properties, and the nucleon number, more specifically the number of neutrons, will affect the the physical state. Okay, now we'll move on to question number 5. The mass of a DNA molecule is this much. So they gave us the mass, they gave us the speed of light, they want the energy. This takes us to Einstein's very famous formula, which is E is equal to mc squared. The energy is equal to the mass of something times the light squared. Why times the light squared? Because you have, for example, an object here, and you're the observer here. The mass of the object, of course, you're gonna multiply it by the time, like by the light speed here, and it also goes back. So like you're multiplying it not only once by the light speed, but also because it's going back, you know what I mean? So that's why the energy is equal to the mass, which is 3.59 times 10 to the minus 15 times C. What is C? C is 3.00 times 10 to the power of 8. All of it is what? All of it is squared. You put it on your calculator. I got 323 joules. Okay, that's it for question 5. We'll now move on to question 6. What does it say? They gave us the mass of the proton, which is 1.672623 times 10 to the power of minus 27 kg. The mass of the neutron is this much. The mass of the nucleus is this much, right? And they gave us what? They gave us the speed of light. They want the mass defect of the lithium nucleus. So the mass defect is what? It's literally the mass defect means the change in mass. That's all they're asking for, okay? The change in mass here in this case, you have to like understand the concept. It is that the mass of the separated protons and neutrons is always greater than the mass of them combined. What does this mean? This means that the mass of the proton plus the mass of the neutron, all of it, it's going to be what? It's going to be greater than the mass of the nucleus, which I will denote by capital M. So the defect in mass, it will be what? It will be the mass of the proton plus the mass of the nucleon, or the neutron, for example, minus the mass of the whole entire nucleus. Okay, so now let's start. They gave us the mass of a singular proton. How many protons do I have? I have 3 protons. So it's going to be 3 times the mass of a singular proton, which is 1.67. 3 times 10 to the power of minus 27 kg. Then, what am I adding to it? I'm adding to it the mass of the neutron. How many neutrons do I have? My nucleon number is 7. So the number of neutrons is going to be 7 minus 3, which is what? Which is 4. So it's going to be plus 4 times 1.674929 times 10 to the power of minus 27 kg. Please do not forget any number. Very, very important. Now, all of this, you put it in the brackets. You subtract it from what? You subtracted from 1.15, which is the mass of the nucleus, 25801 times 10 to the minus 26. So now, you're going to do open your first bracket, 3 times 1.67263 times 10 to the minus 27 plus 4 times 1.674929 times 10 to the power of minus 27. Close your bracket. Okay, minus what? Minus 1.152580 times 10 to the power of minus 26. You put it on your calculator, and I got that the mass defect, which is delta M, it's equal to what? It's equal to 1.91784 times 10 to the power of minus 28 kg. Okay, so that's it for question number 6. We'll now move on to question 7. What does it say? The mass defect. Okay, the mass defect for a carbon-12 nucleus is this. So they gave us delta M, right? They gave us the speed of light. They want to find the binding energy per nucleon of carbon-12. Now, the binding energy, you should know, it's the same like formula for the energy, but here it's delta E. Why? Because before it was E equals mc squared. Here the binding energy delta E is equal to delta M, which is the mass defect, times c squared, right? But pay attention, they want it per nucleon. So whatever answer you get, you have to divide it by what? By the nucleon number. So nucleon number. Okay, so delta E, here it's going to be what? It's going to be delta M, which is 16.43 times 10 to the minus 29 times 3, open brackets, 0.00 times 10 to the 8 squared. Okay, then your whole answer divided by the number of nucleon. It's a carbon-12 nucleus, right? So here they, when they say carbon-12, it's carbon and then the nucleon number. So you'll divide it by what? You'll divide it by 12. So you put the answer on the calculator and you should get 1.23 times 10 to the power of minus 12. Now pay attention. What's the unit for energy? Joules. And then don't forget to write per nucleon. So what is the answer? It's 1.23 times 10 to the minus 12 joules per nucleon. Okay. We'll now move on to question 8. What does it say? A gold nucleus has a mass of 197. So 197, this is the mass number, or no, it's not the mass number. Calculate the radius, the volume, and the density of the gold nucleus, assuming its mass is this much. Okay, so in order to find the radius, the volume, and the density, we always, first of all, we're going to start with the radius. The radius, it has an equation, which is what? Which is R0 times the nucleon number to the power of what? To the power of 1/3, okay? Nucleon number or mass number, they are the exact same thing. Now, R0, if they don't give it to you, it's always going to be 1.2 times 10 to the power of minus 15, right? So R is equal to 1.2 times 10 to the power of minus 15 times the nucleon number, which is what? Which is the mass number 197 to the power of 1/3. You put it on the calculator, I got an answer of 6.98 times 10 to the power of minus 15 meters. So this is the radius. Now, they want the volume. We know the volume, first of all, it's a nucleus. The nucleus, what's the shape of it? It's a sphere. What's the volume of sphere? Sphere 4/3 pi r cubed. So it's going to be 4/3 pi times my radius, which is 6.98 times 10 to the minus 15. All of it being cubed, I got an answer of 1.43 times 10 to the power of minus 42. So now I have my volume. Remember, they gave me the mass over here. They want me to find the density. Density is equal to mass over volume. So it's going to be 3.27 times 10 to the minus 25 divided by the volume, which is 1.43 times 10 to the minus 42. You put it on the calculator. I got an answer of 2.3 times 10 to the power of 17. And what's the unit? It's kg per meter cubed because it's the mass divided by the volume. Okay, that's it for question number 8. We'll now move on to question number 9. What does it say? Naturally occurring chlorine consists of two isotopes, this one and that one. They want us to calculate the average atomic mass. Now here you should have learned this from chemistry. What do? You take the mass, which is 34.969, right? You multiply it by the percentage abundance, but please use the exact answer, so 75.78%. Then you add it to 36.966 times what? Times 24.22%, okay? You put it on your calculator. I got an answer of 35.45 U, okay? So that's pretty much it for question number 9. Now we have the last and final chapter, which is, the last and final section, which is section 1.3, radioactivity. Okay, now, question number 10. What determines the stability of a nucleon? Here you have to think of the binding energy, delta E. The binding energy determines the stability of a nucleon. The greater the binding energy, the greater the stability. You have to remember this. So, again, the binding energy, please pay attention, per nucleon. Here, this is my mistake. Not the binding energy, it's the binding energy per nucleon. The binding energy per nucleon, okay? That will affect the stability of the nucleon. So the greater the binding energy per nucleon, then the greater the stability. Okay, that's it for question 10. Question 11, it says, describe the type of neutrinos you detect during beta minus decay and beta plus decay. Let's start first of all with beta minus decay. What happens in beta minus decay? We have a neutron and 0. What happens? It's like an unstable nucleus, okay? It will get converted into a proton, into an electron, and into an antineutrino. The antineutrino, we will denote it by this. This is antineutrino. Now, the beta plus, what happens? It's the reverse reaction. So instead of the neutron, the neutron turning into the proton, now the proton will turn what? Will turn into the neutron. And now it will release the opposite particles. So instead of the electron, it will release a positron. And instead of the antineutrino, it will release a neutrino, okay? So again, you have to memorize what happens in beta minus and beta plus. In beta minus, you have your neutron. It's decomposing into what? Or not decomposing. It is, let me find a more suitable word. It's unstable. So it's converted into what? It's converted into a proton, an electron, and an antineutrino. But then on the other hand, you have beta plus decay. You have an unstable proton. It will decay into what? Into the neutron and the positron and the neutrino, okay? Now, if you want more detailed answers, this is what they said in the answer key. In beta minus decay, you have a neutron and an unstable nucleus is converted into a proton, an electron, and an antineutrino. The antineutrino is specifically an electron antineutrino. Then you have the beta plus decay. In this process, a proton is an unstable nucleus converted into a neutron, right? A positron and a neutrino. So the neutrino produced is specifically an electron neutrino, okay? So that's it for question 11. We'll now move on to question 12. It says, what's the relationship between the mass and charge of a positron compared to an electron? Now, you should know that the positron and the electron, they're antiparticles of each other. They're antimatter, right? So the positron, E plus, and then the electron, E minus. You should know that they're gonna have. So it will have what? It will have the same exact mass, the same exact properties, but it has what? But it will have the opposite charge. So, opposite charge, okay? So basically, this is what you need to know about the positron and electron, is that they're antimatter. And because they're antimatter, more specifically, because the electron is a lepton, you call the positron an anti-lepton, right? It will have the same mass, but basically it will have the opposite charge, okay? We'll move on now to question 13. It says, list the reasons for the following statements. Why do we say that radioactive decay is random, and why do we say that radioactive decay is spontaneous? Now, to start with, if a radioactive decay is random, that means you cannot predict exactly when the nucleus will decay. For example, let's say you have, let's say carbon-14. You cannot say that it takes the carbon-14 atom to decay, let's say, I don't know how long it takes. Let's say it takes half an hour, for example, you know? You can't specify this, okay? You don't know how long it, like, when it will decay. It might decay right now, right? It might decay in like 10 years. It might never even like decay in the span of your lifetime, you know? But there is literally like no way of knowing beforehand when it's gonna decay, you know what I mean? So that's the definition of it being random. Now, spontaneous means that the decay happens by itself. Nothing else triggers the decay. So, but it does not mean like any extra factors. You know what I mean? Like the extra factors could be light, cooling, pressure, heating, chemicals, electricity, I don't know. All of this is not needed. It happens by itself, okay? So here in the answer key, what does it say? For random, okay, it says that each nucleus has the same chance of decaying per unit time. So remember, each nucleus in a sample has the same chance of decaying per unit time, and it's impossible to predict when a given nucleus will decay. This is for the random. For the spontaneous, we can say that the decay of a nucleus is not affected by the presence of other nuclei, because nothing will stimulate the other. And then the decay of nucleus cannot be affected by changing the temperature or pressure, okay? So that's it for question 13. We'll move on now to 14. What does it say? It says, how can a graph of count rate versus time be used to demonstrate the randomness of radioactive decay of unstable nuclei? Basically, the fluctuations on either side of the count rate. So you have the count rate, it will show you like fluctuations. So the fluctuations on either side, compared to the time, prove that radioactive decay of unstable nuclei is random. So they ask you, how does the graph of a count rate versus time be used to demonstrate the randomness of unstable nuclei? Very simply, you have fluctuation. You don't have like a constant trend. No, you have fluctuation. You have it going up, down, maybe it's increasing tenfold, decreasing by half. You don't know, you know? But the fluctuations, the randomness, show that the radioactive decay of unstable nuclei is random. Okay, that's it for question 14. We'll now move on to question 15. It says, state the mass, charge, and the typical speed of each of the following particles emitted in a radioactive decay. So here I'm gonna make this a table, and please memorize the table. So let's see what I have to deal with. First of all, they want the mass, the charge, and the speed. So I'm gonna write mass, charge, and speed, okay? Let's start with the alpha particles. Alpha particles usually have a mass of 4 mu. How did I know? Because alpha particles are helium. They have 2 protons, but they have a mass number of 4 because they have 2 protons and 2 neutrons, okay? That will make 4 nucleons, okay? Now, usually the charge is based on the proton number, so it's going to be +2, and you have to remember that the alpha particles take about 6% of the speed of light. So here they gave it to be, for example, 20,000 kilometers per second. Now, for the beta particles, they have very light mass, so that's 1/1800 AMU, right? Their charge is -1 because the beta particles are electrons, right? Now, you don't choose the positron as the beta particles unless they specified that it's beta plus, but otherwise, it's always gonna be the electron, okay? Anyways, because the beta particle is an electron, its charge is gonna be -1, and its speed is 98% the speed of light. They didn't give a specific answer, so I'm not gonna write anything specific. And then last but not least, we have the gamma ray. It does not have any mass, does not have any charge, and its speed is the speed of light. So again, alpha particles, 4 AMU, +2, 6% of C. Beta particles, 1/1800 AMU, -1, 98% of C. Gamma ray, no mass, no charge, but its speed is C. Okay, that's it for question 15. Now we'll move on to question 16. What does it say? They want us to complete the following: the alpha decay of this. First of all, alpha decay means I'm dealing with an alpha particle. The alpha particle is helium. It has 2 protons and 4 neutrons. 149 will give me something, right, +4. So what's this something? It's going to be 149 minus 4, which is 145. 64 will give me something +2, so it's going to be 62. So it's going to be 145 and 62 SM. Now, beta minus. What happens in beta minus? What do you release in beta minus? In beta minus, you release what? You release an electron and an antineutrino, right? So here, if you want, you can add, of course, the antineutrino. So it's like a V0 or like this, something like this. But anyways, you're releasing an electron, right? So its charge is going to be -1, its mass is 0. So the mass of Ru is 99, but the proton number, or like Z, which is over here, it's gonna be 43 minus 1, which is what? Which is 44. Okay. Now here for the beta plus decay, we are releasing what? We're releasing a neutrino, and here don't forget they don't have any mass and they don't have any charge. So here it's a positron. So here this is gonna be 12 because 12 minus 0 is 12, and then 7 minus 1. This is plus 1, by the way, that's why it's like this. So 7 minus 1 will give me 6, so it's gonna be 6 carbon 12. Okay, so that's it for question number 16. Now the last and final question, and then I'm done with the part A. Full complete revision for the AS physics is question 17. What does it say? You have the mass of the alpha particles. Okay, let's see. You have the mass of radium, the nucleus of radium. You have the mass of the Rn nucleus, right? And you have the speed of light. What do they want? First of all, let's write the equation. Calculate the energy released when radium-222, so Ra, decomposes, okay, to release an alpha particle, and what? And radon, which is Rn. Now, one thing you need to keep in mind is that the mass of the whole complete one, so mass of radon, it is greater than the mass of the alpha particle and the mass of the radon. Or what is this one called? Yeah, so radium, the mass of radium is greater than the mass of the alpha particle plus the mass of radon. So it's going to be 368.66717 times 10 to the minus 27. Okay, all of it minus, open brackets, the mass of the alpha particle, which is 6.64. And then another 4, and then 6 times 10 to the power of minus 27. And don't forget to add with the mass of radon, which is 362.000679 times 10 to the power of minus 27. Okay, so then you're gonna get what? You're gonna get delta M. This is the most important thing to pay attention to. This is the binding and not the binding energy, sorry, the mass defect, delta M. So you put it on your calculator, 368.66717 times 10 to the power of minus 27 minus open bracket 6.64466 times 10 to the minus 27 plus 362.00679 times 10 to the power of minus 27. So I got the delta M to be 1.572 times 10 to the power of minus 29. So now they're looking for what? The energy released. The energy released is the binding energy, delta E. So it's going to be the change in mass times what? Times c squared. So E equals mc squared, delta E equals delta mc squared. So delta E is equal to 1.572 times 10 to the power of minus 29 times 3.00 times 10 to the power of 8 squared. So 8 squared. So I got an answer of what? I got an answer of 1.4148 times 10 to the power of minus 12 joules. And that's it for this whole entire full revision. Thank you guys for watching. I hope you enjoyed and have a wonderful day. See you in part B. I think part B is, if I did not do the quiz practices for chapter 4, part B will be the last ever video that I'm gonna do for grade 11 material. Oh my goodness, that's so sad. So thank you guys for watching, and I hope you enjoyed, and see you in the next video.